Okay, so this is day 2 of the 2023 Spring UCLA QC Bio Collaborative Workshop 36, Advanced UNIX Scripting and Queuing for Large Data. So let's pick off where we left off. We had basically gotten to the point where we were able to align one piece in an interactive session. And now we want to expand that to aligning all the pieces, which means using the queue system. And we'll first do that a simple way, which is to just do one queue job per part. And that'll work okay for 42 parts. It doesn't work very well for hundreds or thousands of parts. And so then we'll move to the next level, which is the job arrays. Okay, so we're going to get back on Hoffman here. And we're going to go to my scratch space. And there's the workshop directory. And here's where we were. So you see all the parts. We broke it up into the 2 samples into 21 parts each. And it doesn't take very long. These parts are so small, they don't take that long to run. So we'll just realign the one part, which is kind of where we ended up. We already did the alignment like at the end of last time, but just doesn't cost us much time right now just to redo it, and it kind of refreshes you where we were. So that's an example file name of that's the first part to do. And then we, as usual, construct the output file name from the input file name there. So that's going to be the output file name, or the output file name base, because the .bam part is going to get put on by VS Bolt. And so then here's the actual alignment command. We're using, if you're doing more careful about the biology or something, maybe there's more parameters you'd have to specify because maybe the defaults aren't appropriate. But this doesn't really affect this workshop in terms of what's going on inside. We're not doing the actual biology here. So we're just going to use pretty much default minimal options just required to get VS Bolt to align. So that's the reference genome, preprocessed reference genome. That is the single-ended gzip fastq reads as input. And that is the base name of the outputs. And that is how many cores you want VS Bolt to use as it does its work. And then this is the little, rather than running this directly, we run it through this utility, which monitors the resource usage and then gives us a resource usage report. Because one of the big problems with running stuff in Hoffman is trying to figure out what your resource request should be. Because if your requests are too small, things don't work, the job will die. If it's really too small, the job will die in kind of an obvious way. And the queue system will tell you that I killed it. If you give it way too much resources, then you're going to be unnecessarily waiting possibly forever for your jobs to start, and or if they are starting, you could get more of them going at once if you use less resources, because you wouldn't even be competing with yourself so much. So that's the motivation between trying to dial the resources kind of in. And unfortunately, like the memory one is probably the hardest one to figure out. And the memory one is also kind of tricky because when you're kind of in the middle twilight zone between sort of like way too small and way too big, there's a zone where sort of you can get sort of unpredictable, very strange errors that are hard to detect. And I'll show you that because it's actually not that uncommon to kind of have these kinds of things happen, because usually the recommendation in Hoffman for how to dial in the resources is actually start on the too small side and kind of like work your way up and find the point to transition where things are working well. Because if you try to go the other way, way too big and dial down, you are immediately at the situation where you're waiting forever. It doesn't work very well. So you got to kind of work at it from sort of the left to the, you got to find the boundary from the left, basically. So, so it's not uncommon to kind of have weird memory things happen because you are kind of like trying to find that boundary. So that's the way I'll demo it in here. Right. So, okay. While I was talking there, I should have just had this running, so it could have been working while we were talking. But oops. Oh, okay. I didn't run all these other commands here, right? So there was this module load Python. We needed Python, and then we had this virtual environment. The shell error there was like actually the shell started this command because time is a command and time runs. Time is the program that's actually going to launch the VS Bolt. So time started up, but time could not find VS Bolt because we don't have our virtual environment active and all this stuff. So that was the error we got there. So here I'm activating my virtual environment that we created yesterday. And now you see the prompt change to, kind of a hint that's done. And then we also need SAM tools. Actually, we probably won't need SAM tools until tomorrow. I think we'll go to day 3, which was always the schedule for a 3-day, 3-hour workshop. So now we're ready to do this. Okay, so there's the file name, there's the construction of the output file name, and we're going to use 3 cores here. That's what we were doing. Same as our interactive session. Now, if I run this thing, it should go. No, still wrong. Now it's wrong. Oh, cannot allocate memory. Well, that's a different error than yesterday. This worked yesterday. So this is kind of what I mean when there's sort of like kind of spotty enforcement of memory limits and so on. So we sort of know from yesterday that we actually did run this yesterday, and then the resource accounting actually told us it was sort of like 13 and change of memory. But I started the interactive session with 3 times 4 is 12, and 13 and change is over 12. And today, due to whatever node run or who knows the phase of the moon, today we're actually getting a real error that says, so most of the internal heavy lifting in BSBold is just a little Python script basically, is with the BWA aligner, which is one you may be familiar with, that's written in C++. So here's BSBold putting out a progress message saying, I'm calling BWA mem with all these parameters. And then we're getting an error from BWA, which is saying, I can't, I just tried to allocate, was that 6 gig or something? Yeah, I mean, it's probably tried to allocate 6.2 for the forward strands and 6.2 for the minus strands or something. That's 12 and change or whatever. Anyway, that exceeds the 12 that we got for the interactive session, and it actually got it. The operating system said no, and BWA just stopped and so on. And then the rest of this traceback stuff is Python reporting where the exception was raised inside the Python code. But anyway, so that's kind of clear. I mean, there's a lot of noise here, but basically there is a hint there that, yeah, you're running up into memory limits. So actually today, this is not working in the interactive session. And maybe I didn't want to really kill my whole Hoffman session, but maybe I need to, the interactive session, we got to go higher, right? So, well, let's be generous. So let's do 5 times 4, it's 20. Right. That'll probably still not take too long. Yeah, there we go. So you notice with the new session, I'm back to the beginning. Every new shell that isn't started as a subshell of another shell basically is like from scratch. So this is a new shell on a new machine. So it's completely new session. So I'm back in my home directory. None of my module stuff is loaded. My virtual environment's not active and so on. So I gotta do this again. Okay. All right. 3rd time's the charm, right? So so the very first thing the BWA does is probably read in that indexed reference genome. So this pause here is probably during doing all the I/O. It's just sucking in that huge disk files into RAM, and that's what this kind of pause is. And I expect to see in a few seconds, however long this takes, 30 seconds or something, this initial phase. This is then it should give us some more progress information as it actually starts aligning. This is also why you kind of don't want to say cut the pieces too small, right? Suppose you do BSBold aligning 100 reads or something. Well, it's going to spend a minute reading the reference genome, and then 0.001 seconds aligning the 100 reads, and you wasted, in terms of 99% of the computation time was not spent aligning your reads because of that startup phase. So you don't really want to cut the pieces really small. If the startup phase is a minute, it's no problem to have an hour-long job in Hoffman. So maybe you try to target an hour or something, right? Because then Hoffman, there's a big transition around 2 hours, I think, where jobs that are over 2 hours in reservation are kind of treated differently than those under 2 hours, at least historically. That was true. I don't know if it's really still true. I think it's sort of still true. 2 hours, under 2 hours is sort of an easy hole to fill in the schedule, but over 2 hours, it becomes sort of it has to work harder to kind of like block that in and work there we go. So now I think we're basically done reading the reference genome. Or maybe that was just the plus strand and now it's working on the minus strand or something. Or bisulfite, there's actually 4 strands. There's sort of the bisulfite converted plus, the bisulfite converted minus, the reverse complement, bisulfite converted plus, and reverse complement, bisulfite converted minus, because bisulfite treatment changes C's to T's, which breaks base pairing. And so when you redo strands after that, either because of the way library prep works or whatever. Oh, there we go. Now we're actually doing read and reads, reading input reads and stuff. So now we're actually working. So where was I? Yeah, anyway, so there was maybe two pauses there. Maybe one was reading half the half the strands and the other was reading the other half of the strands. Anyway. So I don't think this takes too long once it actually starts the actual read alignments, because our pieces are only 500K. Like I said yesterday, I think in a real, for whatever your project is, you have to figure out what the right size pieces is, right? Here I'm just using VS Code alignment of whole genome bisulfite data in human as an example. But in this particular setup, a typical part size that you might actually use in a real run is 10, 20, 30 million read part sizes. Because specifically to basically target something like half an hour or an hour as a runtime. You would just extrapolate, right? You would run, you run this. We know that this, I think yesterday it took like 4 minutes or 4.5, maybe 5 minutes for this thing. And we just saw the startup phase is like a minute or something. So maybe 500K reads is 4 minutes. So that means 1 million reads would be 8 minutes, and 10 million reads would be 80 minutes, and that's an hour 20, right? So anyway, that already tells you like you should probably aim somewhere around 10 million reads or something, right? If you were trying to actually dial it in, right? So that's how you would dial in the time, right? So the three resources in Hoffman are, I think it's just about done. So are number of cores, time, and memory. Right? So you got to try to dial each of them in, right? So cores we try to keep small because that makes us schedule flexible and allows us to get lots of them running in parallel at the same time. Time, usually you can control completely by the size of the pieces. And so there you kind of run test runs, and then you figure out where you need to go to get half hour, an hour, something like that. And then memory, you don't really have control over memory because it's too small, it doesn't work, and too big, you're wasting resources and making the whole job take too long. So memory is a question of finding out where you need to be, right? So we run the test run within time, which is going to produce the stats soon. Yeah, maybe there's 2 passes for the alignment here. I don't know why time hasn't given us the output yet, unless there's sort of like 2 phases in VS Code. Maybe that was phase 1. Yeah, it looks like there's a phase 2. We have to do some more alignments. So I guess that pause there was probably like, oh, there we go. All right, so anyway, there's 2 rounds or something. Anyway, we'd have to really dig into VS Code source code or something to figure out exactly what the logic is. But we're just guessing here, looking at that. But there we go. So that looks like a successful run of the first part. 500K reads input as seen by VS Code, good mappability. Here is the resource usage as reported by, not that line, from here on is the resource usage from bin time, user bin time. And important numbers are things like this maximum resident set size, which is in kilobytes. This is your peak RAM usage basically, or like I was saying yesterday, there's a lot of ways to measure RAM and they don't all correlate with exactly how Hoffman does it, but we just kind of need to know kind of where roughly we need to be. And this was 13.4 gig here. And any other numbers here that are really important? Not really. I mean, the time here is, whatever. We have some sense of time because we sat here and watched it, but here, here it says the wall clock is basically 4 3/4 minutes. And it was told to use 3 cores, and on average it used 170. So you may wonder, how do you use 174% of CPU? The answer is it's all denominated against 1 core. So this really means 1.74 cores were actively doing work associated with this thing at a time. Why isn't that 3? Well, that's probably because the startup phases where you saw those long pauses where it was reading in the reference genome, those are single threaded. And so we gave this thing, 3 cores? Actually, my interactive session has now got 5 cores, but I think when I reran this thing, I changed this to a 5. But I didn't change this to a 5. I could have, I can run with less than I have, but the reservation is now for 5. So I could have made this 5, but I did run this time that we just saw there was still with 3. So my guess for why that's not closer to 300% is those long startup periods where it's only single threaded. That's kind of moving our percentage down. If the piece sizes were larger, you could amortize out that startup cost more, right? So that's why you don't want to sort of like cut the pieces too small. we're artificially small here just to keep this whole live example moving fast. But anyway, so that's kind of where we were. Another thing to notice is that the time command, which was given, where is it? There it is, right? So this is the literal command time ran, which is bsbolt, which is a Python script. That Python script doesn't do a whole lot of computation inside of it, certainly not compared to the BWA that it calls itself. But we see that the accounting does have sort of like this big RAM number and sort of the full time and so on. And that's because the accounting not only counts the direct process launch, but all of its sub-processes and their children and so on. And most of the accounting, like Hawkins accounting is like that, and the bin time accounting is like that. It includes not just literally the command you ran, but the entire universe of things that it ended up spawning. Okay. So yeah, we basically just talked about this. This is basically, this is our logic for how we decide the initial amount of resources that we're going to run the 42 parts with. And maybe this is our first guess here, or this was, I was making some of these slides to say on Monday. And so I did some runs on Monday, and I have some of those saved here because, as you see, things are sort of non-deterministic on Hoffman. And even if I run exactly the same thing on a different day, it's not going to end up coming out the same way because it depends on what nodes and how they're loaded and stuff. So to have something stable to kind of have on the slides and show you different situations, I do have sort of 3 runs I did on Monday that are saved here that we'll be able to look at because they illustrate different things. And you know, the resources that I chose to run that day, based on the stats stuff here that's over here and we just talked about, is let's just try even 2 cores for the CPU, 7 gig of RAM a core, which is 14, which is a little over 13, and a 1 hour time limit. I mean, the 1 hour time limit it's going to be way too much, right? I mean, but like I say, it's kind of like until you get into kind of past 2 hours, the scheduler doesn't really penalize you too much. So here's basically us thinking about the resources used. This is us basically figuring out the numbers we're going to plug into the Q sub line. The other thing to not forget about is don't forget about your disk space, okay? Because that's another resource, but it's not one you directly talk about to Q sub or the cluster. It's just something that's going to be a side effect of your computation. But generally on Hoffman, you have quotas on your various spaces where you can put stuff, and you know, it's finite. So it turns out, like, if you know, so we got to estimate it. How can we estimate it? Well, you know, we'll just look at, say, the one example that we did and what kind of things happen. So here was the input file, right? You know, so that's the input file, and it's 4.4 meg or whatever, right? So there's like, oh no, it's 44 meg there, right? So there's 44 meg, and here's the output file. We haven't even looked at the output file yet, but here's the BAM, the binary alignment file that came out. And it's actually bigger than the input, which isn't really a surprise because most aligners make the entire input also be part of the BAM file output. Because what's a BAM file is basically the same as the input with extra information about where on the genome the things go. And so basically the output includes a copy of the input. So it's not a surprise that it's bigger. Even though they're both gzip compressed. BAM is a binary format, internally gzip in a special way, but so it doesn't really get a gz extension, but it is basically gzip inside. So anyway, so yeah, so that's how big this thing is. It's like 67 meg or something, right? So you know, if you divide those two, you know, but you know, whatever here, so blah divided by blah, 1.5 in round numbers. So you know, there's a rough estimate. Output should be about 1.5 times input. So what's the total size of our input? Well, that's all the part FASTQBZ. GU disk usage will tell you that. The H means use human units like gigs and megs and stuff instead of kilobytes, probably is the default. C gives you a total line. So how big are all those input parts? And the answer is, you know, 1.7 gig total. So now we can estimate the output size, 1.7 gig times 2.5, or 1.5, 2.6 gig. So we expect our computation of 42 parts to add 2.6 gig to our disk space, which not a big deal today. I mean, this little example is little, but remember, from the original 2 samples, we're currently down to about a 40th because we only took the leading 10.1 million reads. So multiply by 40. So now that, you know, whatever, I mean, we have a calculator, so 6 times 40, that's about 100, called 100 gigs. So these 2 samples unheaded would have been about 100 gigs of output, but maybe you have 20 samples instead of 2 samples, right? Well, there's another times 10. Well, now you're at a terabyte, right? So, and then, like I said, that a terabyte there probably means that your input was also something like 2/3 of a terabyte or something, right? And then, so then you got to hold the input and output. Well, now you're at 1 and 2/3 terabyte, and then we're eventually going to have to merge those BAMs into per sample single BAMs. That's going to be another copy. And so, you see easily how disk space can kind of go, 2.6 gig does nothing to worry about. But when you start doing the multiplies out for what the full job, the full thing would be, it can be substantial. Okay, so how are we gonna, so we've run this. This is how we ran this in the interactive session, basically. This was us running one part in the interactive session. All right, so we haven't used the queue system at all yet. And before we can do Java arrays, so we need to just be able to see how to sort of like run like one command like this using the queue sub job submission system. So that's our next step. So we're gonna pack that up into a little shell script because you don't really want to make a queue sub have a gigantic command line. It's very hard to kind of get everything you want and sort of in the queue sub line. Mostly what you want to give to queue sub is just the name of a shell script. And then when it starts the job on some other node, it's going to run that shell script. Maybe you can put some parameters on that shell script. That's not a big deal. But you don't want to try to have like all the commands in there and stuff like that. So we're going to make a little shell script that does what we want to happen on the node, whatever node queue sub picks to actually run it on. And so here's our little shell script. There's the start of the shell script. It's usually good to have some progress information in the shell script so that you know that like, oh, we started the script, we reached the bottom, stuff like that. So this echo just, is going to print out something like this. I don't know why my internet's really slow today. Whatever. Okay, so that's going to print something like this. The $0 will be the name of whatever the file name of the script is. The $@ will print out all the arguments. I mean, this isn't quite equivalent pasting this into an interactive session. This is something that's going to be set by the script arguments. This is going to be the script's name. We're not really. That's why you see bash -bash. It's my login bash. But you see how the date works and the host name works and so on. Right now, the interactive sessions on the 7041, and so on. So that's just going to print out some progress information for us to help us understand our log files. And then I'm just kind of putting the commands that we had up here, right? So here was our commands, like this kind of stuff right here. I'm going to get rid of the user bin time. We're not going to need that anymore. But so like there's those first 2 lines, and then there's the BS bolt line there, basically. Now, what's the extra stuff? The extra stuff is this open paren, and this, well, then here, but this echo at the end is just more progress. It just matches the beginning thing. So then the rest of the extra stuff is just from here to here. So, okay, what's that stuff? Well, remember that shell scripts in general start with a kind of a fresh environment. And certainly shell scripts launched by the job control system on another node are going to start in a fresh environment. So it's not going to know our Python and our virtual environment that we need to run BS-Bolt. So that's why we have to have the module load Python and then the source of our activate from a virtual environment to set the environment up so that we can actually call BS-Bolt at this point. The shell scripts that the job system starts are started in a really Spartan environment that don't really have hardly anything kind of available. In particular, they don't even have the module system available. And so there's different ways you'll see people get around this. This is a way that I don't really want to talk about how shells do the startup scripts and stuff like this or whatever, but it just empirically, this has worked pretty well in the past. So this little source line just loads one of the Hoffman configuration files that one of the side effects is going to be it's going to make module work, so on. So basically these 3 lines are us getting our shell script environment on the node that's actually going to do the compute, which is a node we don't know yet because it will be chosen by the queue system. It gets the environment inside that shell script to be equivalent to the environment we've been using in our interactive session. So this is to get the BS-Bolt aligned stuff, so that we can do that. That gets the environment ready. Okay, so that just leaves this open paren and this stuff here. I've got 2 commands inside here, and then the open paren here and the close paren here starts a subshell. So that way, when I do the redirections, it applies to everything inside, as opposed to the redirections without the parens would just apply to the the last command in the pipeline. So without the parens, it would just be on the MB and not on the BS-Bolt. So the parens make sure that the redirections apply to the whole thing inside. That explains that. The one bracket is equivalent to just a bracket. That's just us saving a copy of the standard output to a log file. The two greater than sign is a copy of the standard error. So on Unix systems, there's 3 streams that all programs have by default: standard input on number 0, standard output number 1, and standard error number 2. And the convention for programs that have no reason to do anything else, I mean, like, you know, a lot of programs, like, you know, BS Bullet, it's going to read the input GZ file. Well, that's not going to come from standard input, because we give it on the command line in a parameter like this and so on. That isn't going to already be open. It isn't like one of these 0, 1, 2 things. It'll probably be number 3 or something, but it's not standard in, standard out, or standard error. So, I mean, programs can open and close files on their own and so on, but, you know, we have a lot of programs like, you know, like gzip and less and so on and whatever, that, you know, if I take one of these gzip files and I do this and then I pipe it to less, well, gzip is going to open this file. I could even do the redirection like this. Right, so like this. And so what this means is that gzip's standard input will come from this file. The shell handles that. I could also do it this way. This is kind of a stupid way to do it, but it's kind of even more kind of obvious this way. So cat will open this file and then start writing it to cat's standard output. The pipe arranges for that standard output to be gzip's standard input. Gzip uncompresses it and writes that to its standard output, which this pipe connects to the standard input of less. Right, so that's like an example of programs using sort of these default streams of I/O, and the convention for programs that are working like that is that the standard input is where you read your input from. Your standard output is where you write most of your output to, your generic output, and then the standard error is where you write your error messages, progress messages, and stuff like that. And so that is stream 2. Basically, the greater than sign defaults to 1 anyway, so you don't need it there. But the 2 here, if I do want to just say redirect the standard error, that's why I put the 2 there. The less than sign defaults to 0, so you don't have to put that there. But so anyway, so this is us basically keeping 2 log files rather than the messages that we're scrolling by on the screen. If I still have it in the scroll back, yes, we do. So here's an example. We ran this interactively. It started here. And it goes to wherever it went to. Well, we're not going to run the bin time stuff, so we're not going to have this stuff here. But this is basically some mixture of the standard output and standard error of the BS Bullet align run. That's the stuff I want to save in log files. So that's what these 2 redirections are. Okay, so now we've explained almost everything except for this stuff. And this is the pattern we saw on day 1, which is the recommendation to write your output files with some tag like in progress or something, so that after the job done and looks like it completes successfully, you rename them from in progress to done. So it's a little more obvious just from the file name whether they're actually done or not. And this double ampersand is like the semicolon, remember, but it looks at the exit status of this program, and if this program declares itself to completed successfully, then it runs the right-hand path. But if the program on the left doesn't complete successfully, it does not run the right path. Whereas semicolon doesn't care, it always does translate. Right? Any other question? Yes, so good question. So what's going to be the current working directory when this script runs? That's a good question. So we're going to, when we start QSub, there's different options you can give to QSub, but we'll give QSub an option that says, make the current working directory of the thing that gets started when the job starts to be the same thing as the current working directory that QSub had when QSub was run. And for us, we're going to run QSub we're doing everything in this place, right? This directory is where we're doing everything. So our shell is in this directory. The shell starts QSub. QSub is in this directory. We give an option to QSub that says when the job system starts the shell script that I told you to give it, start it in the same directory you QSub are at, which means this directory. So our script indeed will start with this as its directory. And because of that, I could actually do this and it would be fine, because that will be the relative path relative to where we expect the script to go. This means, I write it this way because it means no matter where you are, this command will activate the Python environment. It's more independent. You don't have to think about where it is relative there, but yeah, that's absolutely true, is that I don't really need the full path there because we kind of know where this script is going to be started from. Okay, I think we're done. We're ready. Oh, and then the last bit is, okay, this has got to become a shell script. So the next little business that's here, which is this stuff and the purple box and this stuff and this stuff, is just little ways you can get small files onto Hoffman, because there's like a bunch of them, and you can choose the style you like. Some of them are more or less convenient. Some of them are super fast. So I'll show you one way. Actually, I'll start with this. I'll start with this one. I'll show this one first. That's actually the one I usually do. So how does that work? So what's the name of the shell script we want to make? It's this is going to be the name we want the shell script to have. So I've already got a copy there from playing around either yesterday or this morning or whatever. So I'm going to get rid of it. Okay, so now it's not there yet. Okay, so I'm going to say cat and write its standard output to this place, and then hit return. And now you see it's kind of waiting. What is this? Well, cat is a very simple program. If you don't give it any file names, it reads from standard input. If you give it file names, it reads from those instead in the order left to right that you give them. And it just writes whatever it gets as input to standard output. So here I've given cat no input file names. So cat is reading from standard input. The redirection here means that when the shell started cat, it started cat with its cat's standard output going to this file. The shell actually created this file and then connected standard output to this thing and then started cat. But where's the standard input coming from? Well, we didn't do a redirection for cat for standard input. So the standard input for cat is the same thing as shell standard input. Well, where is shell standard input coming from? My keyboard, my terminal session. So cat is basically trying to read from my terminal session keyboard right now, but waiting. I'm not typing anything yet. So here's what I'll do. I'll put this in my GUI clipboard, right? So this is Keynote. Command C on the Mac is copy, edit copy or whatever. So that's GUI clipboard. I now switch to my terminal application, my emulator. This is terminal.app, and I'm going to paste it. And what that does is that terminal takes what's on my GUI clipboard and pretends that I'm pressing all those keys, right? Very fast and so on. But basically, I'm going to Command V and paste it. Okay. But now I got to sort of tell cat that I'm done, right? Because this could go on forever, right? So we need to give some indication there isn't any more input. And the way that's done is with Control D. So I'm at the beginning of the line here. I'm going to hold down Control D, and that tells basically the system that there's no more input. The way that really works, I mean, just ignore what I'm about to say for the next minute because it's probably too complicated. But the way it really works is I typed in Control D. My terminal emulator sent a real Control D, which is ASCII 4 control code. SSH is the program running on the machine. That's the network connection to Hoffman. So SSH on my side, it's over the network now. Hoffman gets the Control D, the ASCII code 4. There's an SSH on Hoffman's side that receives that. Then there's something called a pseudo terminal, which is the interface between sort of SSH and because these days we don't have real glass terminal screens and real keyboards connected by hard physical serial lines to the machine. And pseudo terminals are how we sort of allow software to pretend to be what used to be a physical cable. And so there's a Control D that sort of goes into that virtual keyboard of that pseudo terminal. And then the pseudo terminal has a driver, which is part of the operating system. And that operating system is looking for Control Ds at the beginnings of lines and turns those into a special signal. And that special signal is what causes cat, which is trying to read from the keyboard, to get a read of 0 length. And that's how cat knows that when cat tries to do a read and doesn't make progress, cat stops doing its little read loop. So end of ignore. But basically, the way people colloquially condense all that is they say that Control D sends an end of file. The Control D is controlled by your terminal settings, which are STTDY. So you'll see here, whatever, somewhere in here is EOF is a Control D. Interrupt is Control C. That's how you stop commands. Backgrounding is suspend. That's Control Z. We saw that yesterday when we were like there's a command I want to put in the background, Control Z. That's where all those keyboard shortcuts come from, is that they're part of the terminal driver settings. And the terminal driver is basically a little piece of code in between the real keyboard and the program, and is able to sort of transform our raw keystrokes a little bit before the program sees them and turns some of those keystrokes into signals. But it doesn't matter anyway. So let me just do that again because you'll see how fast it is, right? So here's the file name that I want to create, at that, Let me grab it. So copy, switch over, paste, Control D, done. Okay, now I have this file here. Cat spam. That is the fastest way, probably in most cases, to get little shell scripts, little bits of text and whatever onto Hoffman. You don't have to fuss with file transfer program or whatever. You're just sort of working in, you can do it in your flow very, very fast. And I usually, here I've got Keynote with my stuff, but usually the way I'm working on Hoffman is I have a local text editor window. I'm on Mac, so for me that's text edit. If you're on Windows, you could use Notepad or Notepad++, or I don't know. There's a million text editors. Take your pick. I'll probably be working on my shell script in my I'll make this a little bigger. I'll probably be working on my shell script. I'm writing my code or whatever, and I'm working on my local text editor because it's a lot more convenient to sort of edit things around in this than this to sort of deal with the Hoffman side. And once I kind of got my shell script kind of the way I'm looking at it, it might be Command A, select all, Command C, copy, switch over here, find the command, the last, bam, paste, Control D, done, right? Fast. So that's one way to get little files on Hoffman. Another way is to use an editor on Hoffman. So maybe I think we showed you Nano in workshop 1. Maybe the 3 most popular editors on Hoffman side would probably be Vim, Emacs, and Nano. And I'm not going to really get into those, but I'll just show you what they look like. So if I was to Vim this file name, here it happens to already exist. If you're creating a new one, it would start empty, but here, and now I'm sort of in the VI editor inside Hoffman. So this is a program running on Hoffman. And so, it happens to know like terminal code, so it can color things and move the cursor around and stuff. So it doesn't quite look like a normal command line program, but it's really just a command line program, and it's just writing terminal output like anybody else and taking terminal input like anybody else. But you have to know all these little commands now to edit. You have to know that I put you in insert mode, so then you can type characters, and then escape gets you out of insert mode. And then luckily the arrow keys work. If you're in the really old days, you got to know like the HJ, what is it? J moves you down. That's been a long time. K moves you up. Whatever. Arrow keys are a thing that didn't exist in the early days of computing, but now arrow keys are around. So that's how you move around. DD will delete a line. U will undo. You got to know all this. Whatever. You got to learn all these codes. Colon Q is how you get out. Oh, but I've modified the file, so it's warning me. Yeah, you haven't saved this thing. Colon Q bang means exit, and I don't care that I have unsaved changes. Emacs is another one, completely different set of keystrokes and interfaces and so on. It looks like this. It's even got like a little fake little pull down menus up here. The only thing I'm going to tell you about Emacs is how to get out, because people get stuck in Emacs very easily. Control X, Control C is how you get out of Emacs. Nano is the friendliest of the bunch. VI and Emacs are entire universes among themselves. Some people even consider Emacs a whole operating system itself. Nano is much more friendly, and very little features, but enough to get you going. So in Nano, you can basically always type. You're always editing. There's no modes like in Emacs or VI. And there's a little help page at the bottom here with the Control X to exit. Control is that an O to write the write the changes out or whatever. So Control X, exit. Save the modified buffer. No. Okay. So that's editing on Hoffman itself, right? So there's no file transfer there. You're just running a program that happens to manipulate files on Hoffman side. So that's this. So that's these two. The third way, which is another way that can be done, is to use what are called here documents. So in the shell, let's see, let's do it this way. So let's see. Yeah. I guess I'll just paste the example I really have here. So this is as it's written in the slides, and I'm just going to paste this. And you see that also worked. Well, and it's hard to believe because the file existed. Okay, the file doesn't exist. Copy, paste that whole thing. The file exists and it has the right context. Okay, so what does this do? This is using a funny redirection called a here document. So, normally redirection is like this, and you'd be looking for this as a file name. But I've got 2 less than signs in a row, and that makes it a here document. And what that means is that standard input is not going to come from this as a file name. Standard input is going to come from the same place that the shell is getting its input, which is my keyboard again. So, I'm entering this as a command line, and essentially these are more commands, if you like. They're just lines going to the shell. This is a line going to the shell. This is a line going to the shell. This is a line going to the shell, and so on, all the way down until here. They're all just separate lines of text going to the shell from our keyboard. I'm pasting them in from my terminal emulator, but it's basically from the shell's point of view. It's just receiving it from the keyboard. The shell's just receiving it from its standard input. And so this means the shell takes to mean as redirect from the same place I'm getting my shell's input from. The same place the current script's input is from. That's where I'm reading. That's where the standard input connection is going to come from. And so then the following lines are just basically being used as standard input to cat. So then the question is, how do you get out of this? How do you stop? Well, you're not going to have a control D or something like that. That's something that's like the keyboard driver does and so on, whatever. And so this is the magic word that when you give this word on a line by itself is what terminates the connection. So you can choose whatever word here, because maybe you have an input that actually has that in here, and now that doesn't work. So then you got to choose you got to choose some other word that doesn't appear in the input, so that way you can cause it to trigger at the right place. Anyway, so that's here documents. All those ways we just talked about have the same effect of just getting our little shell script file up on Hoffman. That's all we're trying to do. Yeah. I mean, the last way you could do it, right, is that you could use a file transfer program, right? Like I could, where's the shell script, right? So I could grab the shell script again. The last way would be, here's my text editor, my local text editor on my local machine. I could save that, on my desktop as whatever file name it's supposed to have, blah, blah, blah. I think I just saved it with untitled 576. I can let you know that actually you can get to 1,000. It'll go to untitled Windows and Mac will go to thousands, and then they actually do use a comma because I get that high. There, so I've saved that file on my desktop, and then I could use file transfer to get it to Hoffman. Right? So file transfer I can do in the command line. I can use SCP, and there's the name of the file. I'm in my desktop right now on my local machine. So there's the file on my local machine. I could copy that to Hoffman. I got to give the path. I can't use tab completion to get the path because it's not on my machine. So my machine doesn't know what the path is going to be. It's this, right? So, and there. SCP really uses SSH inside, and since I have passwordless SSH, that's very convenient because it doesn't ask me for a password. You may be familiar with CyberDoc or whatever. There's GUI transfer programs you can use. It's all good. Okay, so there's a zillion ways of transferring little files around, but probably the one I showed you first is the one I probably do the most because it's just so fast. Okay, so the last bit was, the last little bit is the purple box, which is there's 2 kinds of here documents. It's just a subtle point, but if you do get into here documents, it's worth knowing this difference. And actually, sometimes both versions are useful. Here, I'm just going to set cell variable b to 2 and t to 21. And here, I'm going to, this is the same pattern as we have here, except I got rid of the quote marks here. Okay, you'll see here that there's no quote marks there, whereas this version has quote marks. And so we're just going to do basically the same thing twice, but one has the quote marks around that magic word and the other one doesn't. And then these are shell scripts. We're going to make them executable. Okay, and then we're going to run them. Now, what are these shell scripts supposed to do? Well, they each set B and T to something, which happens to be something different than what it is here. And then they just echo out B times T is B times T. So, kind of if you look at the shell script, you're going to say, well, that's going to echo out 3 times 23 is what is that? 69. So let's run the 2 scripts. There's one, and there's the other. Where did we get no output of the other one? Oh, because something went wrong with the, because I copied a $sign. when I tried to run the other one, I didn't miss the $sign. So we have an empty script for that one. So okay, let's just start right from the beginning. Okay, so there, 1, 2, 3, executable, run. Okay, and you see that they're different, but the text in here is the same. So why is that? Let's look at the inside of those two files, and you'll see the difference between the quoted and unquoted form of this, which is that the quoted one, which is the second one, literally has the text that's inside. But the unquoted one, the shell is actually substituted based on the current state of things when we ran. So the B got plugged in from here because $B expands in the shell that this was running this to 2, and the T expanded to 21, and the B times T expanded to 42. And that got directly put into the there, which is sometimes what you want, but this is the difference. Is do you want the text inside here to go through all the shell transformations and expansions, or do you not want and just want literally this? So okay, so that was a long walk, I guess, for this slide, but it's a lot of stuff going on there. But anyway, the whole point of this, the whole net effect of this slide for future slides is just to get this one file here. So there we go. We make it executable. Okay, so that's our little shell script. Okay, which we already explained how it's going to work inside. So now we want to run qsub to submit this as a job. So what does that look like? So I suppose if you wanted to, we could test in our interactive session whether the shell script works. Maybe that's not a bad idea, right? Because it's not quite literally the same thing we ran at the beginning of today. We should see that the shell script works before we start jobs, whatever with it. So how would we test the shell script without using the Q system? Well, we would just invoke that shell script, and we got to remember what the arguments to the shell script are, which is how many quarters you want it to pass on to BS Bolt, and then the input file name is the second argument. So we did part 1 as a test, right? We already did part 1 as a test. That was the one we started with today. Let's do part 2 as a test. So here's the first sample ending in a 7, and then with part 2. And so this is the line that we want to run. And then we might just try redirecting the output of this thing to standard output, and then redirecting the standard error to here. We could put the user bin time on here, either yes or no, it doesn't matter. We could put it in the background so we can go do other things while that's busy. So we'll start that off, and you'll see I've got, oh, I have an ls-la somewhere. I must have already typed ls-la, but didn't hit enter yet. And so we have a very strange command here. So that didn't work very well, right? Because actually ls is the program that tried to run. So let's try that again. These are the dangers of copy and paste into terminal windows. There we go. Okay, so that's running in the background. And here is the standard error and standard out log files, and hasn't started making the BAM file yet, because I don't think BS Bolt makes the BAM file until the BWA alignments are sort of in flight, and the first stage of that is to read that reference genome, which takes a while. So it's a little while before the output BAM file shows up. So, but anyway, so to really check, I mean, before we would run the Q system, I would wait that finishes and verify that that's working, but it'll work. So let's just go on to how you would submit it on the Q system. So it's not that bad, really. It's just sort of like the stuff we've already seen, but with some extra padding. So let's parameterize it again. So we decided back here, this was our decision, right? We were going to use 2 cores, 7 gig of RAM per core, and 1 hour. That was our decision. So let's put that here. So 2 cores, 7 gig of RAM per core, 1 hour. Jobs in the Q system need a name. And QStat only shows you like 10 characters. So it's to your benefit to try to keep the names short. So maybe we'll call it like bisulfite alignment, the sample whose name ends in 7, the third part. So if this one's working, this test was on the second part, let's make this first job that we run in the Q system be the third part. Okay, so let's put a 3 here. So that we're going to do the third part as our submitted job. Okay, so then what you do is qsub, and then a bunch of options. And then the resource requirements, which you've seen already from QRSH. So how many cores to PE shared, and then the resource string here. So the runtime here, H data per core gigabytes. There's the G there. We put the G here rather than putting the G like into here or whatever. That's because we do arithmetic with that. And the G wouldn't really be helpful there. So we put the G there for gigs, and then we multiply out the task end for task per core gig there for the HDMem and put the G there. Okay, so that's looking kind of like a QRSH line. The things that you don't have in a QRSH line are the stuff in yellow, which is explained here, and the command line that you want to run. You know, QRSH, you're running an interactive session, you're going to get a shell, and then you start typing commands in that shell. Whereas here, we're not going to be interactive with this job when it runs. We got to tell it what to run now, so that when it starts, it knows what to do. And the answer is we want you to run our shell script with this as its first argument, and this is our second argument, which is, you know, exactly the same kind of thing we're doing up here. But here I'm giving part 3 because I want my submitted job to do part 3 as the one it's going to do. And so what's the yellow stuff do? So per your question, -cwd makes sure that the started up script runs in the same directory as qsub is running from. This is the option that specifies that. The -r no, some of these I'm not sure whether you need or not. This is the way I always do it. The r no means that if the job has errors, don't automatically try to restart it. Just run it once at most. The j no relates to the structure of the log files and makes sure that the Q system standard hour and standard output are separate. The MAS says to email me on certain conditions. There's a lot more letters you can put here, but unless you want your email filled up with thousands of messages, I usually just put the really error conditions in here. So the A and the S, the A means if the job is aborted, if the Q system aborts the job, like maybe it goes over time, that's an abort. And the S means if it's suspended, but unless you suspend it or the administrator suspend it, I mean, that basically never happens. But the aborts happen, like if you go over time. So this says the M means email. And so if either of these things happen, you can put more letters for more conditions. Like you can do job start, job finish, you know, you can do a whole bunch of ones, but the AS are sort of like the exceptional conditions. Only if things go wrong, send me email. What email, how does QSub know what, how does the Q system know what your email address is? The answer is in your home directory on Hoffman, put a file called .forward and put your email address as the single line contents of that. And that is how it works. Oh, and then the job name, the -n job name, which, here we're doing this. So that's it. Okay, so let's do that. Let's submit our first job here. Let's see. Okay, so it took a few seconds there. This is the job ID number. This is its name, and it's been submitted. Let's go look at what Q has. So QStat shows you the entire job queue. QStat-U, a username, shows you just the queue for that user. The shell has a variable called user, which is your own name, or you can say, who am I? So this would have been equivalent. There's also basically my jobs, which is basically a synonym for QStat-U, your own name. It's all the same. The QStat without parameters is going to show you the entire queue, which we'll look at in a second because it's useful to get an appreciation for just how many jobs are queued and running on Hoffman at any moment. But you see here, I've run it a few times or separated by a few seconds, and now you see kind of information that the QStat gives you. So this QR login, this is our interactive session. Okay, this is the job number of our interactive session. It was started, basically when we started today at 1:40 p.m. When we started today, this is the 5 slots because remember we were having problems with 3 slots getting the interactive example to run. So we logged out and got a new session with 5. But anyway, this is our interactive session. This is our job that we just queued here. This is the job we just queued here. The BS line 703 with this number 7222906, which is the same one that we got there. And what's the state? QW means queued waiting. Okay, that means it's in the queue, hasn't started running yet. But it's eligible. It's waiting to get scheduled. It was queued at 2:26 p.m. A minute ago, and it's scheduled to use two slots, 2 cores when it gets started. You see later here when we ran qstat again, it actually made it to the running status. Okay, now it's running, and it's running on node 7420 with its 2 slots. And okay, so that done message is the interactive part 2 test of the shell script that we started a while ago, which is now finished. And the part 3 queued job is still running. Okay, so we're gonna let that go for a minute. It's, we can go, node 7420 is working for us now. Let's go look and see what that part 2 was like. And part 2 looks okay. Part 2, this was the interactive test of the shell script. There's the BAM file, looks about the same size as that one. That was good. We could check out we got some stuff in our standard input and standard error logs. Let's take a look at that stuff. So here's the standard error log. Let's look at that. And that's the same kind of junk we usually see out of VS-Bolt Align. Most of this stuff is, some of this stuff is from the BWA subprocess doing alignment. These are some stats from bisulfite Bolt itself, or at least some kind of internal stats that it kind of works through. I think it probably does the input in chunks too. So it's doing like chunks, little mini batches, little things and so on. But anyway, then there's the standard output, which is more stuff that comes from the VS-Bolt Align run, which is mostly now kind of top level analysis level stats out of bisulfite Bolt, like how many reads, the alignment percents and stuff like this. So that all looks good. So it looks like our shell script works. So that's good because we already started part 3 as a job using that guy. So anyway, so this is a good, we're at 2:30, so it's time for a 5-minute break here. Our job's still running anyway, so let's take a short break. How many so you already had often. Then you just find it like what are you like you're on you guys are you like what are you kind of the weapon side, you're doing computation, or I'm not that. I know, but you want to introduce yourself to the others. So what year are you guys? So you're in the lab. This is that. Yeah, project. Yeah. That's the worst. The worst thing is getting a big thing running and having it die in the middle and basically making no progress before you can do the people. I wonder on like some of the natural lab stuff like this, like what fraction of like ends up being thrown away. You know? This is an eternal problem. So storage only, it's very, very hard to keep storage use because deleting stuff in storage means making a value decision with that space, that data is no longer useful. And that's not a free decision. You actually have to evaluate. Like that takes like if you were the person that generated it, you kind of got to look at it. And, I mean, it's just so you have to spend. It's not like only positive benefit to like you have to like spend the energy to decide whether you can delete it. And so there reaches a point where the first time it's sort of like it's too expensive to start looking at which data to delete. But at that point, you are never going to delete data again because that's only going to get worse to decide. As the pile gets bigger, it only gets more expensive to decide what to delete the pile. So once you reach that first moment where you're not deleting things anymore, you're doing. Space is now going to grow forever, and you're going to pay for it forever. It's like quadratic cost. because like you can now pay. Not you have to pay like everything you've done in the past just starts to it's like this. Yeah, it is. So I mean, I manage some storage. I manage about 400 terabytes of storage. I kind of deal with, and then like I'm part of like the MCDB group on Hoffman, and then that has some storage. I mean, every file storage I've ever personally managed or been part of or so on, this is a critical problem. So, I don't know how to solve it. Yeah. So for example, I nominally have like permanent storage on Hoffman due to various groups. I'm in this like 15 terabytes. The 14.999% of it, a key of it is always used. So it's basically useless. So the normal way I use Hoffman, my data is always stored for permanent purposes. Often, it has to be on something that I control. It has to be some file storage I have to control. To compute on some piece of it, I have to copy it to scratch on Hoffman, do my compute, and then copy the results back off. The only way, because shared storage always seems to just go to 100% and stay with it. Yeah, you can try, but it's not like it's nicely integrated into Hoffman files. You can't really like I mean, if you have, it's energy to transfer. I mean, you have to. It's not like transparent. It's like you have to spend energy to transfer. And then Google also has a daily limit. Like you can't push arbitrary amounts of data up to Google every day. For those of you that do use file transfer programs, you mentioned Globus. That's one option. But another one, especially if you like Google Drive, like there's down on AWS, there's all there's Box, there's a million of these cloud things. rclone is the program you probably want to get to know. rclone, so how do you copy files? You've seen me use CP a few times. You saw me use SCP just a second ago for a network copy. The CP is only good for kind of within SCP, like get a copy from the local. There's a SCP will only scale to like a certain number of files. Eventually, the next step would be the program called rsync. You might have used that. That sort of also uses SCP uses SSH. rsync will also use SSH. But rsync will handle arbitrary size files and arbitrary files. It does it very well. You can interrupt it, start it up again later with off and so on. I can't get into the rsync. I use rsync here, but if you say man rsync or something, or look at the Google or web or something, somebody will tell you how to use rsync. That's really convenient for moving large trees around. But the next level of rsync doesn't do your thing because rsync only knows how to do like SSH. The next level is rclone, and that understands like 200 of the cloud protocols. So rclone can essentially do rclone has sort of all the rsync functionality, but it talks to many more piles of things. So rclone can clone like a Google Drive tree into your Hoffman space or from Box to Google, whatever. It understands all the ends, so it can piece it together. That's a program that's worth. If you're really heavily into kind of the cloud storage stuff, then rclone. Yeah, that's the same thing as SCP, really. But yeah, this is a nice one to have in your toolbox. Okay. I'm sure. Let's take a look. I'm sure this is done by now. I hope. Yeah. Okay, it's done. We're just down to the interactive session now. Did it work? Let's look. Part 3, BAM file. Size looks about good. We've got 2 log files here. And you'll also see we've got these files up here, which are more log files. So the way I've set it up, where we've got these redirections here inside of our script, one of the reasons why I do that is it isolates sort of the error messages and logs that happen at the queue level from the error messages and logs that happen at your analysis level, right? So The analysis where the actual task we're trying to accomplish is this BS bolt align stuff and so on. And that's, I'll call that the analysis level. That has been isolated. The messages for that have been isolated here. These are the ones, if I didn't do that redirection, everything would have ended up in these, which are made by the queuing system. But it's very useful to isolate out sort of like the analysis level stage from the queue stage. Because like, first question is like, was there problems at the queue stage? Next question is only then do you sort of want to look at your analysis stage. And you don't really want to have all the queue stuff mixed in with the analysis stuff. It's just easier to keep them separate. So that's the way we've kind of arranged it. You see here that the queue, all of these log files are empty except for this one. So let's look at the content of that one. And you see that is the standard output of my work script. I'll call it the work script. It's a script that we gave to queues up to run when the queue runs its job. That's the beginning and ending that came from these echoes here, because these echoes are outside of this the analysis redirection. This is where the analysis redirection is. It's this part. So what in particular what we see here is that the script reached the end. Well, not only did the script start, but the script reached the end, and there's nothing in between, right? So there's no other error messages here or whatever. And then we can look at the standard error and standard out at the analysis level. And we see the same kind of thing that we saw when we did part 1 and when we did part 2. Now we're doing part 3 here, and that's all good there. So that's our first queue job, right? So that's all good. We just need to scale that up somehow. So just to give you an appreciation for what's going on at Hoffman at any time, if I say QStat, that's going to show me the entire queue, which is everything that's running and everything that's queued. Now, that went by pretty fast. How many lines was that? Almost 7,000. Let's look at that a little more carefully. Here's the top of the run queue. I think it's, I don't know how this is sorted, probably not even by job. It might just be by number of slots, reverse order or something like that. Whatever. So here's a guy with a job running on 256 cores. That's probably not a single machine job. That's probably an MPI job. It's actually using MPI to get the cores on multiple machines. You're not going to have much success getting 256 in the PE shared world. We're not going to talk about MPI stuff. The R here is running. This is the username, whatever he had as the job name. We can see those, but you can see there's a bunch of stuff. Now I'm just going to hit space. We're going to kind of go down this list, right? Remember, it's like 8,000 lines. So, everything you see here is running, right? These are all running. Oh, there's the transition. Okay, so that is 4,500 jobs running, most of which are using more than one. A whole bunch are using one core, but all these are using one core. But then there's others up to 56. So whatever. That's what's running at this moment. Actually, well, not anymore. It's been a few seconds since pizza does list, but when you appreciate the scheduler's job, this is the scale the scheduler has to think about. Trying to meet your resource requirements and all the pending resource requirements, because some of that requires advanced planning to make holes that are big enough to fit things in. That's what's going on. Everything down here, QW, these are the start of the what's queued, but not running yet. And you see that there's some of these entries are in this last column, which if we go back to the beginning, it's called JA task ID. That is job array stuff. That's what we're going to talk about later today. First, we're going to scale up to our 42 jobs by just kind of running QSub 42 times, and we'll see that work. And for smaller numbers of jobs, that's perfectly fine, way to go. Then we'll talk about job arrays. So this JA task ID has to do with job arrays, and you'll see here that what you're seeing is here is this line. Here is a big job array. Actually, the H means held. So for whatever reason, maybe it's because this guy's using too much resources or something, and the administrators put a hold on this. But this is a queued job that's waiting, but it's also held, so it's not eligible to actually get scheduled. It is an array job where the job IDs are going from 1.6 million to 1.9 million, stepping by 49. So anyway, that's a lot of jobs in there. That's kind of an unusual one. This guy is doing jobs 2 to 60, still waiting. This guy is doing jobs 1 to 22, still waiting. This guy's doing jobs 332 to 370, still waiting. 673 to 1345. How about some of the running ones? Do we have running array jobs? Yes. When you see a single number in that column in a running job, that is a job that is part of an array job and is currently running. So this is it's part 680 of somebody's array job. And so you see all these guys with numbers that are various array jobs that are spawning. And what's happening when you see the array job stuff in the queued state, that's the stuff that hasn't been launched yet. And the guy submitted the array job, the range was probably bigger than this, and this is just the parts that haven't been started yet. See, okay, yeah, I mean, so you see some of these are pretty big, whatever. There's 50,000 jobs right there, right? 175,000 to 225,000. It's the same guy, and then he does 225 to 300 and 300 to 340. So between 3 array jobs, he's got, what is that? Yeah, I'm having problems doing the arithmetic in my head. 170,000 jobs or something like that. No, so actually you wouldn't even have to split them here. You don't have to split them. The advantage of an array job is it only counts as one slot. So you're allowed, they change it all the time. You're allowed only so many slots in the queue. It's usually in the hundreds, I think, but it could be low hundreds. Let's call it 200 for the purpose of discussion. So that's one of the reasons why queue subbing individual jobs doesn't work very well. The reason why they don't let you just queue sub all 50,000 jobs as individual queue sub jobs is because it drives the scheduler crazy. The scheduler has to think about all those things all the time. And the kind of complexity of the scheduling problem is sort of super linear in the number of pending jobs and stuff. And so you can't let arbitrary people have arbitrary numbers of jobs, and because the scheduler would just, its brain would explode. So that is why you have a limit, and the limit is like 100, 200, something like this. But array jobs kind of only count one. It's because the scheduler doesn't have to think about an array job as 50,000 individual jobs, because all of those 50,000 jobs have the same resource requirements. They just have a number associated with them. And so in terms of scheduling, you kind of just view the array job as just a placeholder, one job. And if you decide to elect to start the array job, it just kicks off the one guy that it hasn't started yet, and then goes back to sort of waiting to schedule the rest. So an array job does not look to the scheduler like as many jobs as it represents. It only feels like one job to the scheduler. And in fact, it only counts one against your list for that reason. And so he actually doesn't need to split them here. I mean, he has whatever reason he has to split them like this, but there is no way you would be able to have 50,000 individual line jobs waiting, but you can have a 50,000 job array job waiting, no problem. Let's see if we see any other interesting syntax in here. Yeah, something you can actually use. You can actually give multiple ranges, and like this is job 1750. This is a union of a bunch of numbers. Like like this is like 1 to 91 stepping by one, so it's like 1, 2, 3, 4, 5, 89, 90, 91. But you can also do kind of arbitrary ranges. This is job 1751, 1931, 1941, 42, 43, 59, 60, 61. Oh, I'm sorry, stepping by 10. So it's 1941, 1951, and 1961, and then 1981. You get the idea. Okay, so you can express any subset of the integers this way. It's just usually it's you have an x to y, usually stepping by 1. This guy's stepping by 10 for some reason. I don't know. You get the idea. Anyway, this gives you some appreciation of just how big the Hoffman running and queued files are, and the size of jobs some people are running on this thing. We did this already. We checked out the output looks good. I don't think we've ever looked at the BAM files themselves. If you're a bioinformatician, you're going to have to deal with BAM files sooner or later. If you've ever tried to look at them directly in less or something, they are a binary file, and Les kind of knows it and says, "You're really sure you want me to show this thing?" and you'll see that it's just binary data. When there's binary kind of codes in here, like this bracket 8F bracket means there's a hexadecimal 8F. This is a single 8-byte character that happens to not be printable. This is the way Lester shows you those. That's completely uninterpretable. You may know the file command, which uses heuristics to sort of figure out what's the content of a file. Because just because a file is called .gz doesn't mean it's a gzip file. Just because a file's got .pdf on the end doesn't mean it's a PDF file. It's really defined by the actual contents of the file. What are the possible interpretations of the file? And the file command uses a file called magic, which knows like 10,000 file formats and tries to guess based on the contents of the file. And you can, have file here, guess what all of our files are here. And if you look at the BAM files, it says, oh, they kind of look like gzippy. They're a little weird, but they kind of look gzippy. So if we actually do kind of try to decompress one of them with gzip, what might we see? And the answer is, well, that looks a little better. We can start to see some things in there, but clearly this is also not right intended for humans. And the answer is that the BAM file format really is a very complicated binary format, and you're going to need a program like samtools to kind of figure out what's inside. And in particular, samtools view shows you what's inside BAM files. And so if I give one of these to samtools view will basically read a BAM file and produce on standard output a SAM file, which is the file format that preceded BAM. SAM is the plain text original format of a BAM. It's a line-oriented plain text format. And this is basically the contents of the SAM file that BAM file really represents. And the columns mean things like, here's the read name. And then this tells you like the status of the alignment. 4, it means it's unaligned. 0 means it's a primary alignment to the plus strand. 16 means it's a primary alignment to the minus strand of the reference genome. Some of these are the start coordinate. This is like chromosome 4 start coordinate. This tells you some details, like this is 101 base gapless alignment. This is a copy of the read bases. This is a copy of the per base read qualities. These are like the alignment scores. I think here's some AS is the alignment score, stuff like this. Anyway, it's basically, this is details about the alignment. Some of these have multiple alignments, so they have kind of like alternate alignments here. And, we don't care. If you care, you can find the BAM SAM file formats back. I think it's linked in one of the secret links in the PDF. If you eventually click all the links, you'll find the one in there that represents the BAM specification. But that's what's inside like these BAM files. Okay, one of the things we can do is we can ask, the job, we have the job number. So it's kind of scroll, we can still figure out the job number because it's encoded in the log file name. This is the job number here. So if one of the things you can do after job is finished is to ask what were the resource requirements post facto. So we can do Q accounting, job number, blah. And that gives us stuff that's very similar to user bin time, but this is the collection of the statistics that happened as the job ran and finished. And we can now look here. Let's see here. It ran on node 7420. It was submitted from node 7141. It was submitted here, it started here, and it ended here. So that's kind of its life cycle as a job. Wall clock time, 357 seconds. Max RSS, this is the same measure of memory that we saw in the user bin time. So if we multiply that by 1024, there's 13.1 gig empirically that thing used from the job systems accounting. The rest of these we don't care much about. There's another measure of memory. This is, it's really hard to explain. Probably the easiest answer is just of all the memory measures, take the biggest one, and maybe that's a recommendation. So that's one measure. This is another measure that's probably in megs, and max vmem, that's almost 14. That I'm not going to get into the different types of Unix memory and stuff, whatever. But anyway, so I guess the biggest number out of all those numbers there is 13.9. So that would be kind of like the number that we would kind of. HVMM is really against this. In the resource spec to keep stuff. HVMM is really this guy. Okay, so that's good. Okay, where were we? All right, how would we do many of these now? We're kind of ready to go now to the full 42. We have all these test runs scattered out. We've done 1, 2, and part number sample 7, number 1 through 3 is test run. Let's do the full batch of 42. I mean, we could do the batch of 42 omitting the 3 we've already done, but let's just move the 3 that are already done aside. They're kind of our test runs. We'll make a directory runs test and just move all that stuff in there. Those were kind of us kind of just getting ready for the real run. Now we're going to do the real run. Okay, so where were we? Yeah, here's the real run. How would we do the real run? Well, we can basically do the same thing that we did here. Where's the last time we ran something? Oh yeah, okay. I want to take this in 2 steps. We can basically just wrap the qsub command that we just did in a shell loop and loop over all the part files and just run qsub once per input file. All right. Like I say, that'll scale okay. It doesn't scale once you get to hundreds, but that'll scale okay for smaller batches. The mesh, the extra pain that I'm doing here is just to make some very nice job names. So I'm going to make job names that are A for alignment, and then the sample number, and then the part number, because that's like 10 characters and will show nicely in like qstat and stuff. And this is just a bunch of shell string manipulation. Just take the file name apart so that we can make those job names nice. So even before we kind of run the real qsub, here's just a test to make sure that this sort of transformation of the file names works right by just looping over the loop that we planned to do, but instead of qsub, we just echo out the job name just to see if whether this junk in the middle here is working. What is this junk in the middle? Well, one of the file names X is going to be something like this. That's one of our input file names. The double % means delete the largest suffix that matches this pattern. The pattern is hyphen anything. So this basically deletes everything from the first hyphen to the end, which is all this stuff. Okay, so that's all that gone. So now we have this. Then the hash mark SRX means delete SRX if it matches on the front, which it does. So now we're down to this. Then the % means delete on the end if it matches SE. That gets rid of the SE, which stands for single end or whatever. That's something I put there. The NCBI SRI session is just this part here. But anyway, so now we're just down to the number part. Then that's good. That's the sample number basically. So that's that part. That's that part. The job name is going to be A that. But then we need the part number too. So the part number, we go back to the original file name X. We pop off the .fq.gz on the end. So now we're down to this. And now we need basically, we could say, strip off the longest prefix that ends in anything dash part, say. That's what this does. Longest prefix, anything dash part. And so that's going to strip away all this stuff. And that's going to leave us with this. I mean, there's a lot of ways we could have done it. Right? We could have done it by character position or whatever, because we know these file names are very structured or whatever. These are a little more reliable because they're kind of based on semantic parts of the file names or whatever, but it doesn't matter anyway. So then that's the part number, and then we just make the job name as A sample name underscore part number. Right? So, and then we just test that out by putting that in a shell loop with all the file names and just echoing out that, see if the job names are going to come out right, and they do. So that's that. Right, so then we're going to do the obvious solution, which is to just call qsub once per part. So wrap a shell loop around it. So here we are, this is our shell loop, but here's the qsub command instead of the echo. And everything is just exactly as it was as we ran the part 3 test case. I don't think any characters changed here. And maybe the file name was here literally instead of as a variable name or something like that. Basically, this is just literally exactly what we've already tested out. So let's do it. Let's launch all 42 here. So, bam, bam, bam. Okay. And you can already kind of see another problem, which is that it's not like qsub is the fastest command in the world. It's taken like a second per job to submit. So if you have 10,000 jobs to submit, that's 10,000 seconds just in the submit. That's what 86,400 seconds in a day. 10,000 is a ninth of a 10%, ninth of a day or something, which is whatever. It's more than an hour. It's anyway. And like I said, the other problem is that you can't put 10,000 jobs in the queue. You're going to reach job 203 or something, and you're going to reach your queue limit, depending on how many leaked out and started running, whatever. So yeah, this is maybe up to 100 jobs. This is a reasonable approach. But beyond that, you're going to have to switch to job already. let's see, are the job numbers consecutive, or are we fighting with somebody else to insert more jobs? That's another cute question there. Looks like we're consecutive right now. So if somebody else was also submitting jobs right now, these numbers wouldn't be consecutive because these are just serial numbers. This is basically job number 7.1 million since the last reset of the system, which I don't remember when that was. This isn't like since Hawkins history. This isn't big enough to be Hawkins' whole history. They reset it. No, it looks like we were the only ones submitting jobs at the moment at near 3 o'clock p.m. But now if we ask for the queue for our jobs, it's a lot bigger than it used to be because now we got 42 guys sitting in here. Now in the time that's been elapsed already, we got 4 of them are running and the rest are waiting. How are we doing? It's been a little while. Well, we got a little more running, but you see how this goes now, right? So now I'm pretty optimistic hitting QSTEP this often to see this much change. I mean, it needs a little more. Things don't happen that fast. So they're just impatient. Anyway, we can let that go. But this is basically one approach, and for this 42 size problem here, as we literally have it, this is going to work. You can see that's actually some of them have already started making their BAM files. They're all marked in prog, remember, because our script doesn't make kind of rename them until the end. And some of them are probably still in the startup stage. They haven't gotten around to making their BAM files yet. But we can also kind of, because of the way we've structured this, kind of also, we don't have to do QStat to kind of see what's going on. We can also just kind of do LS to kind of see what's going on, because we can kind of see which ones are done and not done, but whether the in prog is there, and then kind of whether the BAM, whether there's standard error and standard out, that tells you kind of whether it started or not or whatever. So we're up to part 7.10 has kind of been launched. Anymore? Well, 7.11 got launched now. So anyway, so it's gonna grind for a little bit. So while that's going on, so I was probably making these slides later in the day when closer to end of the day, like around midnight or whatever, it gets less busy, at least for submitting. So when I was writing these slides, like 33 started like right away. You see, it's a little slower now because we're in the middle of the day. So it's not quite so easy to have them just kind of start in that. It's a little slower starting now. But like within a few seconds, like at 11 p.m. or whatever, 33 of them were running. This says I was doing this one at 9 a.m. or whatever. But anyway, that's the beginning of the day. So it's the same thing. Middle of the day is the worst. But here was 33 running, and very quickly all 42 were running. And 42 means 84 cores because there were 2 cores each. And the 7 times 2, 14 gig of RAM, 14 times 42 is 588 gigs of RAM. So, very easily that you're using, personally, you're not going to probably have a 588 gig RAM machine and 84 cores. And so that's the advantage of Hoffman, is that it just has enormous amounts of compute. We're not doing as well in the middle of the day here. So in the middle of the day, we've got this many running, which is what? Oh, that's not going to work in Hoffman. That was a GUI 14. I should. Yeah, I'm not sure if I should tell you that. What I just did there was I copied from my terminal window this stuff into my GUI clipboard, and then on my Mac shell, pb paste is a command that produces the GUI clipboard's current contents on standard output. It's a bridge kind of between the GUI world and the command line world. And then I just pipe that to WC for its opening. I have 15 lines in my GUI clipboard right now. The other direction is also useful. So like here's an LS. Let me go someplace less noisy, or just do date or something, right? So here's date. I could pipe that to pb copy. That's the reverse direction. Take command line standard input into pb copy, place it onto GUI clipboard. Now, if I go to my text edit window, something I hit paste, that's from the command line world in my GUI clipboard. Not very interesting for date, but whatever. Anyway, those commands exist on every platform, but they're not always spelled the same. So on the Mac, it's pb paste, pb copy. On X Windows and Linux and stuff, is it like X cut cell or something? I don't know. There's a whole bunch of them. You just got to kind of, whatever your environment is, you got to figure it out. But if you kind of are working in both the GUI world and a terminal session in that world, it's kind of nice to learn that command or whatever, because then you can kind of bridge the two worlds. You can bridge the clipboard and the command line standard input, standard output with that, and that's pretty convenient a lot of the time. How are we doing? All right, so what we're going to do is let that run, but I have sort of 3 runs of that I did on Monday. And so those are in these directories here. So like there's this day 1 first, that's the first time I tried to run all 42, and then I reran nothing. I didn't change anything, I just ran them again. Day 2 second try. And then both of those are going to turn out to have problems, which we're going to talk about next. And day one third run is going to fix those problems and so on. So let's look at the first one. So I'm going to change directory into there. And this was basically the output of the first time that I ran all 42 in exactly the way that we're doing right now. It's just that kind of this is, because it's non-deterministic, to show you precisely the thing that I want to show you. I just want to show you exactly what happened on Monday. And I can't rely on that happening interactively today because it's a different day with different nodes and different loading on the nodes and so on. So, all right, yeah, so we talked about how bigger jobs are going to need Java array, but okay, so yeah, so here's the big question is, did they really succeed? Okay, so they all look like they're done, right? So here we're looking at what looks like 42 BAM files, and they're not named in prog.bam, and that looks kind of like they're done, but here's the thing. You really, in bioinformatics, the basic rule is anything you didn't check is false. All right, unless you verified it for sure, there's a good chance it's not true. So, yeah, we should check and see whether these runs really did finish and so on. And let's look. So, yeah, so the first thing we can do is maybe ask, first of all, are all the files that should be here, right? Because we ran 42 parts. There should be 42 BAMs, 42 standard error logs, 42 standard output logs. There should be 42 of these. We get 4 of these log files from the Q system for each job, an EO, a PE, and a PO. So, I mean, there should be 42 of everything, right? So let's just check to see if missing files, right? First question. That's pretty easy to do. We can just loop over various extensions, use a shell pattern to ls, and a shell pattern to just list out those guys, -1 to put the files on a single line each, pipe that to wc-l to count the number of lines. This just puts the extension and the tab there just to make the output look pretty. And then do that here. And that tells us that, yeah, there's 42 of each of those guys. And then the reason why I do these 2 in 2 batches is because the EO, PE, POs have a very different pattern than the other guys. And so it's unique to just do these guys separate ways. And then this says, oh, you've got 42 BAMs, et cetera. So yeah, the file counts are all right. No problem. Looking good there. What about the file sizes? That's another indicator that's easy to look at. So the ls command takes a capital S, and that means sort by reverse size. You see me use LSLA a lot. I almost never do just like a straight ls. I just don't find that very helpful. The ls-l I find more helpful. And the A, make sure you see hidden files, which are the ones that start with dot. I don't like it. We don't see any reason by default to really hide any files. We just kind of know what's there. So yeah, so when the size column is here, and you see here it's sorted by dictionary order on the file name, but if I do a capital S, that's reverse sort on size. So that's like this here. So but that's, we need to look at the size in groups, right? So here is looking at the OE, PO, PEs, each as a group by size and descending. And what we see is the .Os, they're not empty, they're all the same size. Okay, so now it's a question of contents, I guess. The E's are all empty, the O's, POs are all empty, the PEs are all empty, so there's nothing to look at inside there. So but no size outliers there for those. We got some non-empty ones to look at contents of later, but there's no size outliers. Let's look at the BAM files themselves, sort by size. Well, they seem to, all these parts are roughly the same size, except for 21s we expect to be smaller because they're 100K instead of 500K reads. So these are all, kind of varying around maybe a range we might expect. But then, and then clearly there's some outliers, right? So clearly kind of the outliers are here, except 2 of these are part 21s. So those we expect to be smaller, and we expect them to be smaller by like a factor of 5, right? Because it's like 100K versus 500K. And if sort of the middle range of these guys is like 65 meg or something, 65 divided by 5 is 13. So we'd expect something like 13 meg for those 21 parters, and that's right where they are. So those actually aren't a size outlier. They're just exactly where they are because they're partial parts, final parts. But part 1 doesn't look good, right? Part 7.1 is a 500K, but why is he like less than half the size of the other guys? That's suspicious. And then 7.5 and 7.9, those look like basically empty. That doesn't look good. So we're very suspicious about 7.15 and 9. 7.1 looks like a partial run, and 7.5 and 9 look like a failed run. What about the standard outs? These are all the same, except down here, there's a little difference. And what is it? Well, the part 21s are a little different, which is easy to believe because, you know, probably some numbers in there are a little less digits because they're less runs or something, but the other ones that are here are 7.15 and 9 again. What about the standard error stuff? Okay, these are all about the same. And then here's where kind of like these are a break, but the 21s are here. Okay, fine. But then 7.15 and 9. So by file sizes alone, we're now suspicious of 7.15 and 9. Now we start looking at the contents. Okay, so let's look. You know, we've got these two system log files. We've got those. We got to look at those. So we can look at all of those. Okay, there's the first one. There's, you know, these are bunches of them here. Well, that's all looking pretty much what we expect. Beginning and ending, nothing in between. We could actually kind of like cat them all together and then sort them and then pipe that to less. And that kind of gives us a more easy way to kind of compare them to each other. And then we see that kind of like, yeah, that's all the lines that are there, beginnings and ends. That's it. Nothing weird there. We could count how many beginning lines, you know, we're being pretty pedantic at this point, but you know, there's 42 beginning lines. There are 42 ending lines. And if you remove the beginning and ending lines, there's nothing else. So that's exactly what we expect. So those are all fine, nothing to see there. Then there's the BAMs, the standard outs and standard errors. Let's look at the contents. Let's look at the standard outs. Well, if we kind of scroll through here, those are kind of, at least structurally, look okay. Maybe the numbers that are most interesting there would be the total number of reads. This is just the count of the input reads, the device level vote reports, and the mappability. So why don't we cat those all together, all right? Sort them unless. This is another way to kind of just check what kind of patterns are in those files. And we just see kind of the lines group, but this kind of makes it a little more obvious that there actually are some problems. Because when we get to like, well, by self ambiguous 0 versus non-zero, that's a little suspicious, but this is the more suspicious number, right? Here's all the mappability percents. And what do you see? Like 94, 93, 93, 93, two of them are 0. That's not good. Total number of reads. Most of them are 500,000. We expect there should be 2 of them that are 100,000. 2 of them are 0 and one of them is 198,020. That's not good. And that's probably corresponds to the 2 guys that are 2 empty BAMs and the partial BAM. We could grep out the mappability and total reads lines and give the file names directly to grep, because one thing that's nice about grep is that when you give grep file names, it will prefix the match with the file that produced the match. And if it's going to a terminal, it even will limit the terminal sequences that cause the different parts to get colored, I think. Here we can see, now we can look directly at set and see that the 0% is 1.5 and 1.9. And the short guy is 7.1. It's, you know, we're building a picture here, right? So that's looking more and more like what the situation is. Let's look at the standard errors. Okay, well, okay, so this is kind of the, you know, that's what they look like, but you know, because it's kind of hard to see that, we'll just cat them all, sort them, and then whatever, because this groups similar lines together, and now we can kind of more easily scan for sort of like lines that look weird. These are like the mini blocks, so like the number of reads here is not really part to worry about. We're looking for kind of like error messages and stuff. Well, there's one that doesn't look good. Seek and qual are a different length. That's Sam, which is probably a subpart of BWA, complaining that like the input FASTQ isn't like properly formed or something. What else? Oh, yeah, here's some more kind of bad stuff. This looks like some kind of BAM error, like the header lines of the BAM isn't right. Another SAM parse error. You'll notice here actually like these W's. This is, I think, the way that BWA reports the warnings. It's the leads with a W or something. That I think the earlier one was an E for error. I mean, this you have to know a little bit about the program or whatever, but even without the program, you can sort of, you don't have to know much about the program to know things that like parse error, line, whether it doesn't sound good or whatever. So we could actually grep out like all the lines that start with a bracket W or a bracket E or have the word truncated in them or so on. And so again, what we see here is that 7.1, 7.5, and 7.9 are the guys that are the ones that contain those weird looking standard error lines. So we basically now examined it and concluded that the run number 1 is partially broken. Maybe the other parts are okay. I mean, they are, but 7, 1, 5, and 9 didn't make it. But we got no messages from the Q system that there were problems. And our little BS Bolt align ampersand MB also made it to the end. So BS Bolt didn't report any like status code that there was a problem. But clearly from the log messages, there's some kind of problem. And I mean, just from the file set, I mean, there's a, it's broken. So what happened? Okay, so this isn't that unusual. Okay, and the explanation basically comes down to the fact that a lot of bioinformatics programs like BS Bolt and so on, which is really just a Python script written by guys like you guys, they're not like super robust software. Okay, so what's happening? I'll just tell you. Basically the punchline again, which is basically that BS Bolt is calling like this helper program, BWA, but not bothering to check whether BWA completed successfully. It's just eating that error. And so what's happening is that BWA is running out of memory. And it's not like the Q system recognizing that we're violating the error. It's that some of the nodes aren't enforcing the memory limits well, and they have other people's jobs running on them. Or ours, which are actually a little bit over our, because right now we're using 2 cores. We asked for 2 times 7, only 14 gig of RAM. And we're floating right around there, and some of our jobs are actually over. And other people's jobs are also running on these nodes, and some of them are over, and some of the nodes aren't really enforcing memory limits. And so some of the nodes are overloaded. Some of those nodes are out of physical RAM. And when that happens, the Linux operating system activates what's called its out of memory killer, the famous Linux OOM killer. And then Linux kernel makes a decision about somebody has to be sacrificed. So it looks at the list of processes that are running now. It has this complicated scoring system, which is mostly like how much memory you're using. And the guy at the top of the list, bam, right? So he gets just killed in a very abrupt way. The process has absolutely no chance to respond or anything, whatever. Now, normally that would cause the Q system to realize that that happened. But because BS Bolt is the one that spawned, the Python script is the one that spawned this BWA, and because BW Bolt realizes the way it calls in Python the subprocess, it kind of gets the fact the error propagates back to BS Bolt. There is an exit status from the operating system that says your child just died, and it died in an abnormal way. But BS Bolt does not check in the Python code what the status is. It just reacts to the fact that the job stopped running, which is expecting. It just assumes that that's the end of the alignment side of the WA. And so then BS Bolt just continues on its merry way. And if the error, if the BW gets killed very early, it just produces 0 alignments. And BS Bolt just thinks you're not aligning anything. You just got no alignments. If the job gets killed in the middle, then you got however far you got. But BS Bolt's basically just going to say, no problem, because it just doesn't bother to check. It just assumes that when BWA finishes, that's the you're done. You got your alignments. Let's proceed. So the fact that it eats the error means that it itself doesn't report kind of any top level error messages that say I had a problem. And it means that the job queue system doesn't get that message. And it means that our ampersand MV proceeds because BS Bolt lied and said everything's fine when in reality it isn't. But that's kind of run of the mill for a bioinformatic program. So, I'm not like inventing some artificial situation here or like picking up BS Bolt as an especially problematic program. This is just kind of like normal stuff, a more normal level of kind of like people write, you know, a lot of academic software is written so that when it work in the case where everything works, it works. But a lot of the error cases aren't well handled. Right? So this is why you have to check kind of in detail, like we just did. Are there problems with the parts? And then react appropriately. So, I told you what the ending was, but what were the hints? Well, the hints were we had a partial run and 2 early failures. Kind of the hint that BWA, which is a help. We know that, I mean, if you know a little bit about the structure of BSBolt, you know that it kind of uses BWA inside. And so some of the error messages talk about BWA. I mean, even if you don't know BSBolt uses BWA, you might just know generically BWA isn't a liner because you would have used it yourself, because it's very commonly used aligner who just reads to genomic reference genomes. And then you see BWA messages inside your logs, and you're like, oh yeah, probably BSBolt is using BWA as an internal aligner or something. So that kind of gives you that idea. And you know that BWA is going to be the big deal. That's going to be the big memory part of the stage. You know, what BWA is the thing that's actually going to look at the reference genome and do the hard computation. And that's going to be the big round stuff. The next hint is that if you just literally rerun the failed parts again with no changes, they sometimes work. Now that tells you that it's sort of like a non-deterministic thing. Right? So now it depends upon which node it's running on and what maybe other stuff is happening on the cluster and stuff. And that's another sign that it's some kind of resource problem or whatever. The way you would rerun the failed parts is just by doing the same loop that we just did to issue all 42. But instead of the 4x in the full pattern, you would just do the 4x in the parts that didn't work, right? So you would just do, you know, I don't know if our run that we have running live today is done. Actually, we have all the parts are done except one, but you know, that for loop with around QSUB that we used to submit all 42 parts, you just change what the for loop is over. So here, instead of doing, you know, the SRX star or whatever, I'll just put the full thing with the 7 there because it was only the 7 guys. And then I'll use this brace notation, which expands, you know, 01, 05, 09 in braces, just expands into everything to the left, all those pieces, everything to the right. So it's just, you know, left 01 right, left 05 right. Yeah, you can just echo it here. You'll get the expansion, right? So there, so you see how that expands. That's actually a pretty cool feature, this brace expansion. So like you can do like, it's even nested will work. Empty strings will also work. Whatever. So that expands into every possible combination there. So the very first one would be ABC, take the first choice, D, E, F, P, and then the first choice E, and that's the first one that comes out. But if you kind of work through all the combinations there, that's exactly what that expands into. That's called brace expansion. It also does fancy cool things like this, like you can do like 5 to 60. That'll do that. And it'll even understand leading digits if it's a recent enough batch. So you could do 005 to 021 or something, and it knows what you want. That's how you would rerun parts. Okay. And I'm not going to do it, but like I did that on Monday, and the parts sometimes work again. So there's your hint. So yeah, so this is the theory in purple that I already just told you about, which is that BWA subprocessable hits some kind of resource limit and it's being killed, not by the job queue system because we'd get messages for that, but probably, you know, next actually be the Linux OOM killer on an overloaded node, and then probably be BSBolt's not checking that subprocess completes successfully. And we can actually verify that theory. I mean, this is kind of more advanced to actually verify that's really the theory. But what we could do is we could look at the log files and pull out the nodes that were problematic. So because if we look at, you know, our log files here, the last word of the first line is the node number that the job ran on. That's like one. There's a lot of ways we can pull out the node number, but that's an easy way to pull them. So here we're just going to do a head-n1 to get the first line, and then an awk $NF to get the last word on that line, and then we need to do it for parts 1, 5, and 9 of the A101-207 jobs. And so these are the nodes that ran the problematic parts. And then here's something you should never do this, which is direct SSH to a node outside of the job queue system. So I could SSH to node 7041. Now I'm being bad, but I just got to be very careful to clean myself up and not leave like jobs running and stuff on this thing. So dmessage gives you the Linux kernel level log. Those are the messages out of the kernel, all the Linux kernel stuff. Okay, and a lot of this is very technical garbage you don't care about, but even at the end here, you see, what do you kind of think you see? Killed process BWA, out of memory. Scrolling up a little bit more. Come on, it's got to be here somewhere. BWA invoked OOM killer. All right, well, now we see. Now, I don't know if this was me or not, because we'd have to correlate this. This is the number of seconds since this kernel was booted. And this node has been up for 41 days, 49 minutes. So we could like calculate 41 days, 49 minutes. And that's a certain number of seconds. And then subtract that from May 3:23 p.m. and find out what time this node was last rebooted. And then add this number of seconds and find out the actual time that this log message represents. And then correlate that against when our job was running. I'm not going to do that. But, and because this node may have run somebody else's BWA now, but believe me, these dmessage messages are us. Okay, so if we grep out like BSBolt and BWA from that dmessage stuff, we're going to see that like, oh, we've got two. Notice 7041 had two of them, 1 and 5, and we got 2 times BWA invoked OOM killer separated by a certain amount of seconds here. That's us being killed twice there. So that kind of confirms that. We could check the other node 6003 as well. So in that we're in there too. So that's basically proof that the OOM killer killed is the reason we kind of saw that. The last thing to verify is, does BSBolt really not check BWA finished successfully? For that, you'd have to dig into the Python source, which I'll show you the relevant parts here. And the answer is, yeah, it doesn't check. So like we didn't do BSBolt index, but there's 2 places that BSBolt runs BWA. One is the index reference you do when you do BSBolt index, which I already did for you when I gave you the pre-index genome. The other is the BS align standard for BWA. So in the index function, it just does the subprocess run, but does nothing with the result. So it just executes the command and just doesn't pay any attention to anything about the status. This is the alignment part of the stuff. There's this launch alignment thing, which is the common function, which leads to align by sulfite with the command line, which chase that function down, which leads to calling this class by sulfite alignment and processing with the command line, which we go look at that code. And eventually we get down to the section here, which is the loop that it opens that ends up opening BWA and piping it to a BAM recompressing helper, but it runs 2 subprocesses, which are helpers, and then it kind of is in a loop feeding data in between them and checking what their status is and so on. But if you look through this Python code, well, it seems to kind of refer to return code and stuff like that. It just uses those to tell when the processes stop, but it never uses the value of the return code to actually decide whether they completed successfully or not. It just runs them, and when they finish, it just moves on. So it has no, it will not report to you whether it's subprocess succeeded or not, and BSBolt's own exit status will not reflect whether it's subprocesses succeeded or not. So it basically just silently eats any errors out of its subprocesses, and that's what the, so it's why do you do that to us? But like I say, that's not uncommon for bioinformatics software. They're usually not very super robust against error conditions. Well, some of them could simultaneously be on the same node, or some of them could be eventually on the same node just later in time. It just depends. I mean, no, it's just an independent thing. I mean, it's just so I mean, okay. So then I did a try number 2 where I just ran exactly the same thing again. And we'll just skip to the end there. And those had different parts fail. Part 7.123 failed. But actually, the error messages are different now. And in fact, actually, the logs actually have more explicitly messages like failed to allocate memory. So it's also a memory problem, but it's more obvious this time because there are actually explicit memory error messages in the logs. So anyway, but the lesson is that the root cause here is really that 7 times 2, we had 2 nodes, 7 gigs around each, 14. It's just cutting it too close. It's just not enough. Either us ourselves are kind of floating around over that limit, or other people are floating over the limit or whatever, but we need to increase the amount of RAM we ask for, because either it's ourselves that are kind of part of the problem, or other people are. But by telling the scheduler we need more memory than we kind of ask, we're kind of giving ourselves some ballast that we can give to other processes that happen to be on our node. Like if I say, oh, I really need 30, but I don't need 30, I need 10. The scheduler still thinks I need 30. And so I start running, and the scheduler has given me the 30. If I use 10, that kind of like is a scheduled 20 that then we can sort of let float around to anybody else that's sharing the node, and kind of act as like an absorber for like other people being over their limits. So, so sort of like, this is what I mean when I said it's kind of like, because you don't want to really find the resource usages from the right, kind of too big and work down. You want to start too small and work up. And we did go to the trouble of running an interactive session and getting some idea what we thought the memory usage was, but we were just cutting it too close. So, which isn't that unusual to find the limit. And when you're cutting it close, what happens is weird things. You either kind of run out to like the Linux OOM killer, or you get weird kind of non-deterministic behavior. So anyway, when there's no other, some of these messages do help you kind of conclude it's a RAM problem. But if you're kind of really at a blank in the end of what it is, kind of the default thing to do would be to just try to increase the RAM limit, right? I mean, that's kind of like one of the first things you would ever try to resolve the problems that you're having. And so that's good. What's going to solve the problem here is just simply just ask for more resources. We don't want to go too far because that's going to inhibit us from doing well. So, but maybe we'll go to like 4 cores, and stay at 7 gig a core, because that'll be 4 times 7, which is 28. I mean, that's twice what we asked the last time, which was 14. But now we're asking for 28. And when I ran that, try number 3, that works perfect. Okay, that didn't have any problems at all. So basically the solution was a single character change, right? Task and cores used to be 2, and now I made it 4. And you may think like, well, why should the number of cores mean anything? Well, in this case, it didn't directly do anything, but it means that the HVMEM gets multiplied out, product of 7 and 4 instead of 7 and 2. And so the total amount of HVMEM we're asking for there, and the H data, well, the H data stays the same, but the HVMEM basically increases there. And that made all the difference. Right? And so all of the non-determinism went away, and all the jobs succeeded first go. I mean, we almost succeeded by running tries number 1 and 2, right? Try number 1 failed on 7, 1, 5, and 9, and try number 2 fails on 7, 1, 2, 3. But that means we could take 7, 2, 3 from run 1 and 7, 5, 9 from run 2, and then we're just left with 7, 1 is broken. Well, maybe we did it a third time even without increasing the resource limits. At this point, you could just pound run 7.1 and just hope you get lucky once, right? Or maybe you increase the resources just for that one, right? You don't have to rerun the whole batch just because one part dies. You just, once you reach like, we're like more than half, a decent fraction of the jobs have finished successfully, you start hammering, you start hammering on the ones that haven't finished, and you just try to like process of attrition and just try to get to the point where you got them all done. And maybe you keep bumping the resources up each time. You don't have to start the whole job over again every time, right? And since we have an embarrassingly parallel problem, we can sort of make incremental progress. It's easy. If you have more problems, maybe your situation was like that, where the internals are more tied together and whatever, and if it dies in the middle, you kind of really got to start at the beginning. Well, that's unfortunate. But in our case, if a part finishes, and we don't have to revisit it. So we can kind of like ratchet. As soon as we get some parts finished, we can just start focusing the rest of our energy on the parts that didn't finish, possibly increasing resources until eventually you get them all done. But you see the games you can play. But in this case, if we just started from the beginning with bigger resources, it would have worked fine. And so maybe that's the lesson anyway. So the run here with just increasing the number of cores to 4, so that 4 times 7 is 28. That worked fine, great. You check all the, so if you can look here. So we've got all the, where are we? So we're currently in the top level. Here's the third run from Monday. Here, let's look at the BAM file size. Sort by size, BAM, and you'll see here that they all look okay. 68, 68, whatever, and then the 213, and there are 42 of those. So that's that. even just the BAM file sizes were indicators of run one and run number two being having the bad parts. And so on. We were pretty careful there. We inspected all the log files, and we did a pretty good job there of looking for where the problems were. And in general, that's what you do have to do. But and also in these cases, just looking at the BAM file sizes would have already kind of told you which were the parts that had the problem. And I'm just showing you that the BAM file sizes here now for run number 3 look good. Now we have our own run that we did today, which is I think still a 7x2 run, right? Isn't that how we started the runs today? Let's check history. Where's our submission of those guys here? Let's go back a little bit. Here we're looking at the outputs of the here's about where we start make runs tests. That's where we moved the test runs aside, and then we're about to the launch was with the 2x7. So the ones we ran today were actually with 2x7 14 and should sort of be on the edge. Let's just see today what happened, because I think they're all finished now, right? Yeah, we just got the interactive stuff. So today we got lucky. Yeah, today they all worked. So anyway, okay, so that's 3:30. So 3:30. So we'll take another short break, and then the next step is to talk about Java arrays, how you would scout up. Because at this point, we basically solved the problem at the sub 100 job level completely, like how to do a loop and like submit all the Q sub jobs and how to verify that they're correct, how would you deal with failed parts and so on. And basically, this has solved the problem for sub 100 size parts. Now the question is, what do you do when you're beyond 100 parts or something? So that's the Java array stuff. So that'll be the next hour. Yeah, so the core files, there's a couple places where those can be turned on or off. I don't know what the defaults are. Yeah, a core file is basically the entire content of memory of the process that you could use a debugger to attach to and kind of find out where was the program executing the code at the moment it died, and what was the data and so on. You don't care because you don't care about the internal program. So that's what the core file is. If you're like a programmer and you're the one that wrote the program or something, and you want to like debug and stuff, that file is basically the image of the thing at the moment it died. So a debugger can attach to that and sort of help you figure out kind of where that's the core file. But yes, if the queue system is the one that kills the job, it certainly lets you know. Yeah, like either you'll get the email if you ask for your board, or you get the Q log. You'll know. Or the QACCT, if Kill County will tell you, killed by. Yeah, so but the why is a more question. Yeah, so yeah, I mean, if the queue system kills you, I think the queue system will even tell you what was the reason. Not really, it just says aborted. Yeah. Yeah. Like I say, the default thing to do if you reach a situation where you kind of have an error that you can't figure out why it's happening, it's probably memory is your first thing to try to do. Because that's the one that creates the most strange situation, because basically what happens is some process just exploded like instantaneously, like right, there wasn't any chance to react or write an error message or anything. It just, the operating system, it just 1 minute it was running a CPU instruction, the next minute it's dead. In the next micro nanosecond it was dead. I mean, it's very abrupt, and depending on the chain of things that created that process, whether they propagate that status back all the way or not, is going to control whether it's sort of like you see it at the top level or not. Here we see the default meaning, the chain for us is like, Q system, our shell script, BS full, QWA, and down in here, this guy ate the return status. And so we don't see it at that point in the chain. And so we're left to infer what happened by a weaker method. I would generally recommend suspicious things, kind of, especially things that just, I mean, the biggest hit is like it explodes in the middle. So at least if you get like some output that it's like truncated or something, there's your hint that things just exploded in the middle. So that's probably a resource limit with hit. But like, what are the resource limits? Time, memory, disk space. Disk space is going to be probably pretty obvious, because if you're out of quota, you can't create any files at all. If you're out of time, you probably know, because like, when you started it. I mean, it's a little more obvious. You know what the time limit was and so on. And the memory is the one that's the most weird. And so there's your guide. Okay. All right. So we've basically now seen two ways of using Hoffman, which I'll call styles. One style is the one we just did just a moment ago, which is to do a multitask job. Here we had 42 tasks, individually submitted as separate QSub entries. That's one style. I'll call that style 2, actually. The other style is even the more basic one, which I'll call style 1, which is just give commands into an interactive session. That's the most basic way of using Hoffman. I suppose there's style 0, which is giving commands into a login node, which is a style you're not really supposed to do much of anything with. Although I'd say the one kind of set of commands you're really allowed to run on an login node is you could run QSub on a login node. That's okay, because that's all right. So when we reach some of these loops that just do QSubs, you don't really need to be on an interactive compute node to really do the QSub loop. I mean, maybe it's a good idea anyway. It's never going to hurt. But you're not really doing hard computation on the login node by doing QSub, unless you're doing a crazy set of QSubs, but whatever. Anyway, so maybe we'll call it style 0. But the question is now we want to do job arrays, which are how you're going to scale beyond 100 jobs, say. So job array. So I already kind of primed you for this a little bit, because when we first started looking at QStat, we had this discussion about the JA task ID column, and we were looking at some people have job array subjobs that are running, and when we get down to the queued section, around here or whatever, you see guys that have queued job arrays with certain ranges and stuff pending and so on. And I told you a little bit about how those work, and so it's basically what we're doing here. All we got to do is know how do we create those things, and then how do the job numbers work? Because obviously the shell script that we write that's going to run has to have some knowledge about the job number to be able to know what to do. Because for us, the job number is going to control what input file you process. And so if the queue system is all about job numbers, but our script is all about file names, input fastqgz file names, something's got to bridge those two worlds. That something is going to be our shell script, but how does it do it? Right? So we got to talk about that. So the first thing is, how do you tell QSub you want an array job? And the answer is very simple. There's an additional command line option called -t, and then you just give it the spec for what you want the job numbers to be. And usually that's just an integer x to an integer y, like 1-10 or whatever. But the full syntax, I think, is anything that you basically have seen in this column over here, which can involve, I don't know if I can find one of those guys, maybe one of the guys with a comma. Yeah, there's like one of these here. Like here's a fancier set of ranges, but you get the idea. Yeah, so x-y represents, 1-5 represents 1, 2, 3, 4, 5. It's inclusive on the endpoints. Very commonly, the first endpoint is 1. we talked about the advantage being while the y minus x plus 1, the number of subjobs, can be very large, the job only counts as 1 against your number of queued jobs, right? Because from the scheduler's point of view, it only needs to think like about an array job as hard as it thinks about an individual job. Array job doesn't, a 50,000 sub job array job does not feel to the scheduler like 50,000 jobs. It only has to think about it as hard as a single job. So that sub job, that array job will sit in the queue in waiting state. And every time it comes up for eligibility for running, what it will do is it'll kick off the next guy that's the earliest guy that's waiting on the list of unlaunched guys, and then the list of unlaunched guys will get smaller, right? And so the array job will sit there in QW with a slowly shrinking list of unlaunched job IDs, and then your running list will have individual guys with individual job IDs, and as soon as they finish, they'll go away or whatever. And how many of those you have simultaneously running at a time can float over time. It just depends on the evolution of things. And then eventually, once the array job has launched all of the task IDs, the array job itself will disappear from the queue state or whatever. You may still have array job, the members may still be running, but that's the life cycle of the different guys that you'll see in QStat. Each subjob runs exactly the same command line in the usual way that you give it to QSub. So when we look at one of our QSub command lines, like wherever was the last one, like here's our QSub command. Here is the way we've done it. We list our shell script, and then the arguments we give to the shell script, I'll call that just the command you're asking QSub to run. Well, in an array job, they're all going to run the same command with the same parameters. So then the problem is, how does the subjob know what to do if they're all running the same command with the same parameters? Because there's the job ID. Where does that come from? Because unless the script can find that out, how does it know what to do different? And the answer is that there are these things called environment variables, which we haven't talked about yet. We'll talk about that in a second. They're very related to shell variables, but they're not quite the same thing. If you like, they're shell variables for general programs and not just shells. But basically, the SGE, Sun Grid Engine, UG, Univa Grid Engine, the queue system, when it starts one of the subjobs of the array job, that subjob gets started in an environment where the environment variable called SGE underscore task underscore ID, all in capitals, is set equal to the task ID number that guy's instance is for. And our jobs are always start with a shell script. And when shells start up, they basically import all of the environment variables into shell variables of the same name. So in our shell script, this environment variable will turn into a shell variable automatically. We don't have to do anything. This environment variable will show up in our shell script as a shell variable, SGE task ID, same name, that will happen to be set to your task ID number. So that might be, you are task 1, or your task 3, or your task 41 or 42. And so our script has to use that shell variable to, for example, select the input file name. That's what we're going to have to do. The queue system basically just manages an integer for you. You got to turn that integer into the rest of the parameters that are varying for you by some mechanism. Okay, so what are environment variables? So we've talked a lot about command line programs, bash itself is one, cat, ls, whatever. They're all taking command line parameters. There's all these command line parameters. So here's ls running with 2 command line parameters. The first one is this 3-character string -la. The second argument is this, whatever this is, more characters. So programs get, so that's an array of strings is the command line arguments to a program. Every program gets that. But what you may not realize is that every program gets actually 2 arrays of strings. So there's one is the command line arguments, which we've talked a lot about. The other is what's called the environment. And that is where environment variables come from. The environment is also just an array of strings. They're conventionally always, probably like alphanumeric characters, equal sign, whatever characters. And they're conventionally interpreted to mean that the thing to the left of the equal sign is the variable name and the thing to the right is the value. And you kind of think of them as like variables. I mean, they're just strings and pass the programs on strings, and programs can interpret them how they want, but that's the convention most people follow. The program env will dump out what the current environment is that env itself gets. Now, where do environments for programs come from? We'll talk about that in a second, but just to give you an idea of kind of what's in an environment, we'll just run n here. And you'll see it's quite a bit of stuff in this environment. But this is probably from when I did module load SAM tools. So there's this environment variable SAM tools bin, which is the path where SAM tools is. More kind of even more basic things in here are like the library path, which is another kind of thing related to the module system. But path itself should be in here. And that's maybe I'll show you the end on my local Mac machine because it's smaller and yeah, it's a little more basic here. It's a little easier to see. So one of the things that's in here is the path, right? You know, that's a very important shell variable because that's the way the shell finds command. You know, when you type ls, shell knows how to find that command, even though ls happens to be in user bin ls. You know, on Unix systems, there's, if you look at the path on Hoffman, say, I'm just translating colon to new line to make it a little easier to read. You know, these are like some really standard places where programs are found, like user bin, user sbin, user local bin, user local sbin, ulocal bin, ulocal sbin. You know, I've got some in my own directories here. There's some of these ulocal s. That's where our Python 373 is from the module system. There's our virtual environment bin directory there. Anyway, if you look in like /bin, there's a whole lot of programs there, and some of them probably Bash itself is in there, right? So, you know, there's du is in there. I saw it go by. Yeah, you can see there's quite a few commands in here. Oh, there's a bzips and the C compiler. Oh, whatever. It's a long list. User bin will also be a long list. Anyway, you don't have to care where things are because the shell has this path, and then when you say ls, it just finds the first place that it you know, it just goes down the path until it finds it, and that uses that, and then you don't have to care where it is, which may vary from system to system anyway. So it's kind of nice to not have to give the path to all the commands. That's the kind of information though that like it's not like you'd have to want to specify everything in the environment as like arguments to every program. Like that would be really not fun, right? So it's not like, you know, what are some other environment variables here? Well, there's like my username, home directory, what my default shell is in Bash, because there's like common shells are like Bash, CSH, TCSH, KSH, the corn shell, there's the Z shell, whatever. There's a whole bunch of shells. Bash isn't the only one, but Bash is very common on Linux. It's the standard one in Linux because it's GNU BASH, and Linux is all about the GNU userland. It's the default for programs, basically. There's my username and stuff. This is all stuff that's sort of like also parameters and arguments to programs, but they like don't change very fast. These are things that are mostly static for a whole session or whatever. So that's why you sort of have command line arguments, which are sort of the rapidly varying, every time you run a command, those are probably changing stuff. And then you have like sort of like the session oriented kind of more global configuration kind of stuff like path and stuff like that. And so when programs run, they're actually given these two arrays of strings, the command line arguments and the environment. And most programs, when they start other programs, the environment that they start subprograms in is exactly the same environment that they were themselves started in. That's what will happen if you don't really ask for anything different. The only programs that typically change environments are shells. And what shells do is that when they start up, they usually import every environment variable into a shell variable of the same name with the same value. And then they mark all those as things that came from their environment that the shell itself is called with. Then as your shell stuff runs and so on, you're creating and deleting more shell variables. Well, fine. When the shell goes to run a subcommand, like you type ls into your shell and shell has to start the ls command, the shell constructs the environment for ls. And the way the shell constructs that environment is that the shell takes the current values of all the variables that are marked for export and puts those into a new environment, and that's the environment it starts the subcommand with. So for example, if I change the path as a shell variable, the next time I run a command, a subcommand, that subcommand will get the changed value of the path from the shell variable, because the next command I run, the shell will reconstruct a new fresh environment for the exported marked variables, and the path is an exported marked variable. And then you can export more, you can add more things to the export list. So like if I do like export ABC equals 42, well, okay. If I set ABC equals to 42, that's an ordinary shell variable. And now if I run end, it's gonna produce a list, but I don't wanna have the whole thing go by, but I'll just rep for ABC. And you'll see that there is no ABC in that list. Because ABC is an ordinary shell variable, not marked for export. And the shell will not construct it into the environment for subprogram. But if I say export ABC equals 42, now end will skip that, because now that variable shell variable is marked as export into external environments. And the next time the shell has to launch a command, which in this case is end, the shell will put ABC equals to 42 somewhere in that array of environment for that command. So that's how environment variables work. So SGG task ID is basically added to the environment of the shell that it starts up to run the shell script we give it. It injects this SGG task ID equals 5 or whatever into the environment of our shell that's going to run our shell script. And then that shell will import that into a shell variable called SGG task ID. And then inside of our script, we can use that shell variable. So that's how that game works. But there's a lot of ways to, so that's sort of the general plan. But then there's a lot of ways to do the detailed implementation of that. So I'm going to show you some options for how to actually implement that. Because basically your shell script has to take that SGE task ID integer and turn that into the variable parameters that you really need to actually run the meat of your script. And there's a lot of ways you can do that. And so I'm going to demo a bunch of ways to do that. We're not gonna try to run like real alignments or something to demo. It's just going to make things unnecessarily cloudy. So we're going to pretend that we have like two analysis pipelines we need to run, and one of them is just called pretend complex command 1, and you just pretend in there's a bunch of commands calling a bunch of bioinformatics software. And pretend complex commands 1 takes 3 parameters, 1, 2, and 3, and the third one is the file name of the output file name. And the actual script that we're going to run is just going to echo back, pretend output, echo the parameters back out into an output file out / whatever the third parameter is, just to create like a fake output file. Okay, so, but in reality, that would be the bioinformatic grinding of probably parameters 1 and 2 to produce file 3, right? So something like that. So just pretend something's in there. Maybe this is a star alignment of RNA-seq reads to reference genome. And then pretend complex commands 2 is just a second pipeline that runs after the first pipeline is done. Maybe this is some R code that reads in the results of the alignment and does an RNA-seq differential, whatever, some kind of analysis. So pretend complex commands 2 takes 2 parameters, 1 and 2, and number 2 is the output file. Pretend that number 1 is the input file or something. And then we want to run that 3 times. We have 3 tasks, but maybe you have 3,000 tasks or whatever. But just to keep it simple for this purposes, we'll just say we have 3 tasks. And so we want to run basically the two pipelines one after another like this 3 times with 3 different sets of parameters. So we want the first pipeline to run ABC1, ABC2, ABC3, and we want the second pipeline to run DE1, DE2, and DE3. Okay. And so given with our little pretend guys here, we're going to get 6 output files in this case with these little pretend contents like this. This is exactly what we expect to run. And we could just literally run this in an interactive session exactly as it's written here, and this would be what would happen. And that is the style 1 way of using Hoffman to do something, okay? But then we're going to use this pretend setup to see how would you do this in the different ways, including a job array way. Okay, so notice that some of these parameters are going to be what I call constant parameters or constant variables, which is kind of a nice phrase. And some of them are variable variables, right? So like the purple ones are the same in every run. The orange ones are the things that vary in this case. And this is a common situation where sort of some of the parameters are things you kind of want to set like globally for the job, like maybe like the path to the index reference genome or something. And then the other parameters are things like individual file names for samples or something, and those got to change. So the former is like a purple and the latter is like an orange. So here we're going to have a bunch of examples. We're going to switch to the terminal to see these, but this is sort of a summary table of what the differences are between these different styles. So these styles I've just arbitrarily numbered as 1, 2, 3, 4, 5 ABC, and 6 ABC. And we've already done style number 1 forever. That is just directly inputting commands into an interactive session. We've also already seen style number 2, and that's using QSub to individually submit each task to the queue system. What styles 3 to 6 are about is using job arrays. So that's this column switches from no to yes here. So if like one of these slides. So yeah, so this is a slide that says we've already done these. These are what we're going to be new. And then the 3 to 6, the main thing that they do is they switch to using job arrays. But why are all these styles here? And the answer is because there's 3 basically parts to deal with. There's the actual commands that run the pipeline. So that's like these, like this pretend complex 1 with stuff and pretend complex 2 with stuff. These are sort of the commands that run your pipeline. That's one set of commands that have to show up somewhere. The next set of things that have to show up somewhere is you've got these constant parameters, they have to go somewhere. And you got these variable parameters, they have to go somewhere. And there's basically all kinds of ways to organize where these different parts go. So usually for anything except style 1, you usually have 2 shell scripts always that are present. One which I'll call the submit script, and one which I'll call the work script. Let me skip ahead here. So this is basically the script that we ran to submit all 42 jobs, right? So this was the shell script that actually did the alignments. This is the little test BS alignment 1 part bash that we made. And then this was the commands that we actually implemented directly into an interactive session, but this is the one that had the loop around QSub and actually submitted them all. So basically this test BS line 1 part bash is what you would call a work script. It is the script that's called once per task to actually do the real work, or start the pipelines up and so on. So here in the box here in the middle is sort of the commands that actually ran the alignment pipeline, if you like. It's more than just the BS bold align, because it's like we had to set up the environment with that, the module load stuff, and we constructed the output file names and the input file names. You could consider that part of the commands that are really part of the pipeline. So this was basically the work script. And we didn't literally put this in its own shell script and so on. We just put them directly into a shell at top level. But this was basically what you would call the submit script. This is the thing that calls the queue sub and gets them into the queue. And so that structure of having sort of a work script and submit script, that's pretty much always going to be the case when you use the queue system. You always got a submit script and a work script. But then whether you have additional scripts or additional files for these variables and stuff is depends on how you want to structure things. So one option is to sort of make a whole shell script for every job, and then arrange the array job to simply call, depending on the job number, you just name the shell scripts basically by the job number, the task ID 1, 2, 3, 4, 5, and then basically the work script just takes the SG task ID and just starts up the shell script with that task ID. Right? And so you basically just repeat your entire pipeline commands with the parameters that you want for each job into its own shell script. So you just have, if you have 10,000 jobs, you got 10,000 shell scripts now. That of course brings up the problem, how do you create 10,000 shell scripts? But whatever, you can imagine the shell for loop that's job is to write shell scripts. But that's one way to do it. And that's very flexible because each of those scripts don't even have to run the same pipeline, right? That's just like each script could do anything completely separately or whatever. It's just sort of like completely independent. So that's what I'll call style 3. There'll be style 4, and that's where we move the commands for the pipeline. Really, we just keep it all in the work script, but the parameters we'll put into config files. So job number 1 will have a plain text file with the lines corresponding to the parameters for that job. And job number 2 will have another text file with the same lines, but with different contents on those lines, with a different set of values for the parameters for that job. And so basically the work script will go look up from SGE task ID which config file it should pay attention to, and then it will read that config file to load up shell variables and then continue on with its pipeline. And that's how it'll do its business of changing what it does based on SGE task ID. That's style 4. The style 5s are about, instead of having one config file per task, you have a single config file for all the tasks. So now, instead of having just one column, now you maybe have the rows are for the tasks and the columns are for the variables, right? So you might have, now it's like an Excel spreadsheet basically, and you can often construct a config file in Excel, say. And so, maybe, parameter, we got A, B, C, D, E. We have, those are our parameters for our little demo situation, right? You know, so this is our demo situation, right? So we've got A, B, C, D, E is basically the 5 parameters we need to run our 2 pipelines. So that would be our columns. You know, it would be the A column, the B column, the C column, D column, E column, and then the rows would be our tasks. We've got 3 tasks here, but you can imagine, you know, lots of columns, lots of rows, right? And now the work script has to be a little fancier. The work script has to use SGE task ID to go to that line number, right? So if SGE task ID is 37, the work script has to go to the 37th line of the single config file and then parse out the tab separated values there as A, B, C, D, E, but then it can then run the rest of the stuff. So that's another organizational style. That's actually maybe the first one that's kind of nice because we no longer have anything, you know, we don't have like a zillion shell scripts anymore. We don't have a zillion config files anymore. We just sort of have one config file, which is kind of like an Excel spreadsheet that just has all the parameters in it. So that's kind of convenient. We'll call that, that's style 5. What are the differences between 5A, B, and C is basically where do the constant parameters go? You could either put the constant parameters in every row, like you have our constant parameters were A, B, and D in the demo. You could put an A, B, and D column in the config file and it just happens to have the same value in every row. That's perfectly fine. That's 5A. The other thing you could do is you could move the constant parameters on since they aren't changing per row. You could stick them in the submit script and the submit script could pass it to the work script, or you could stick them in the work script directly, right? And then that's that. And then your config file would only have the variable column, right? And then the config file will only have the C and the E column that change. So whether you decide to put the constant ones in the config file or in the submit script or in the work script, that's 5ABC. And then that leaves the 6 series as sort of the last flavors. And what's the choice for the 6s? The 6s make the choice to put all the parameters for all of the tasks into the submit, what I'll call the launch. There's what I'll call the launch of the thing. So the submit script is the thing with Q subs. The work script is the thing with the pipeline commands. But there's one more command to run, and that's how do you start the submit script, right? So when you're sitting, at some point you're at a login node or you're at an interactive session, and you give the command that causes the whole chain to start, right? So like either you call the submit script or whatever. There's the command that starts the whole thing in motion, right? So that I'll call the launch, right? So for all the styles that we've talked to so far, the launch is basically going to be just start the submit script because the submit script basically already knows how to do everything. For the ones that take a single config file, it's actually convenient to make the submit script take a single argument, which is the config file's name. That way, that single submit script can be used with any configuration. You just give it different config files and can do different things based on the different config files. But the version 6 style is the one where we pack all of the parameters for all tasks into the launch itself. And so the submit script doesn't really have a config file or anything, and the work script doesn't have anything. It's all comes from the top when we kick it off. We put all the task parameters on the command line that kicks it all off, and they just get filtered through the chain down to where they need to go. And then the variations for 6ABC are the same variations as 5ABC, which is do you factor out the constant parameters or not? And you keep the constant parameters at the launch point, or do you put them in the submit script, or do you put them in the work script? So these are all these different styles that we look at. Now these you can actually follow along on your own session very easily, because unlike all the data files that are needed for the alignment stuff we've been doing, these are like totally self-contained and independent in very small files. So if you run the CP command, you will copy the directory tree that contains demo files for all these different styles into your own Scratch directory, and then CD into your Scratch directory. And then you can follow along with me if you like, and it'll be just fine. So I can do that here. So like back to Hawthorne. There we go. That copied all the demo files, and now I'm actually outside the workshop directory and back into the top level of my Scratch directory. This is where it would show up for you too. And I'm working in sort of my copy. I just copied from myself to myself, but this is a different place. It's sort of my working copy of these style demos. Okay. So now we're going to switch to live session. The slides don't cover this part. So now we're gonna look kind of at these. So here, there's one directory for each style. Remember, style 1 is the very basic style, right? So let's start with that one. So here's the 2 bash scripts, which are the same in all the examples. These are just our little stupid little pretend pipelines. Okay, there they are. And then in this case, style 1 is super simple. There's just one other thing that I've got as a shell script here, but this one is just sort of a placeholder for what you would actually just put into your interactive session directly as commands. Style 1 is just directly give the commands right through your interactive session, right? So we would just literally do that. And then if I look at the output directory, there are the files, and there are the contents exactly as we expect. So I mean, that's we've been doing that in and out all day, every day. That's just maybe the default interaction method for often. Style 2 is to use the qsub to submit each task as its own qsub job. Okay, so the 2 little fake pipelines are exactly as they were, but now we have a launch command, which is the thing you're going to put into the interactive session. Then you have a submit script, which is the thing that calls qsub, and you got the work script that actually does the work. Okay, so the launch is just going to be basically, you're just going to directly call the submit script. So that's what I'm going to put here when we run this thing. The submit script looks like this. Where's that? So here's the submit script. And here, rather than doing the qsub in a loop or whatever, I've chosen to make this qsub basically a shell function and then call it 3 times with the parameters like this. So here is the job name. It's going to be S2 examp, and then it'll just suffix a digit 1, 2, 3, 4, 5. This will become suffix, _1, _2, _3. The way we're going to handle that is with shell variable that we initialize to 0, and then every time you call submit 1, it'll increase that by 1. And then it embeds that into the job name here. So there is the job name. So that's how the job name will just go _1, _2, _3 automatically. These are very small examples. So I'll just put the time limit to 10 minutes, 2 cores, 4 gig per core. I mean, it's way overkill, but whatever. There's no real computation we're doing here, just those tiny echoes. And then here's the submit function, which mostly just bumps up the current job number, and then just calls qsub with the the usual stuff that we've seen here. So the job, there's that, including the job name, construction, task, and cores, their usual resource requirements, and then we just pass this. Everything that you put in submit 1 goes in the place of where the rest of the qsub command would go. So basically, the arguments to submit 1, the first one should be the script name that you want qsub to start, and then whatever arguments you want to give that guy. So we just call, this is task 1, this is task 2, this is task 3. They are going to call the work script, and then here are the parameters for that particular invocation. And then what does the work script look like? First thing it does is just pull out those parameters, and usually your parameters in the rest of your pipeline have real names and real meanings and stuff. So I wouldn't recommend sprinkling kind of like, well, parameter 1 is A and parameter 2 is B. I wouldn't recommend using directly like 1, 2s, 3s, 4s, 5s and stuff all down here. It's just, it's very hard to read. And then if you insert or delete a parameter, you'd have to change everything here in a consistent way. It's just so what you do is at the beginning of the work script, you just pull out the parameters and whatever the current order is, assign them to names that make sense. And then in the rest of the thing, you can use the names as they make sense. So kind of in our little fake example, the parameters 1 to 5 are A, B, C, D, E. And so we just pull out $1 to 5 to param A, B, C, D, E. And then when we do the pipelines, we can use the names that kind of make sense there. And then we just call the 2 pipeline commands that way. And so there we go. So we can try this out. So we can run, anyway. Yeah, so this is the submit, this is the launch command. That's basically just start up the submit script. And you can see that it injected 3 guys into the job queue, and they should be very fast to run. There we go, done, okay. And now you see we got all this logging garbage, which is all empty in this case. And then in the out directory, we have, I think I've already run the test for all of these. So I moved all the garbage from the test runs into here. So that's why these are the ones that we just made live. These are from the test run that I moved into here earlier. But here we have our C123, E123, and there they are. They, of course they work. So that's style 2, and that corresponds to basically the way we did the batch of 42 already. So let's look at maybe style 3. Okay. So style 3, there's our stupid commands again. So what's the launch script for 3? Style 3's main organizational principle is a complete separate shell script for every task. Okay. So here's the launch. The launch is just going to call the submit script, right? So that's the command we're going to paste directly into our session to kick it all off. Here's what the submit script looks like. The job. So now this is the first time we're going to use a job array. Okay. So now the job is just a single job name. There will be a single job ID and whatever. So it's just S3, style 3 example. The 3 here means that there are 3 tasks to do. Okay. We could write this script in a bunch of ways. Like we could have it count the number of, like we could count the number of task files or something, whatever. But in this case, we'll just keep it simple and just say we know that we created 3 task scripts and they're called 1, 2, and 3. Okay. And so end task here is 3 because there are 3 scripts to run and they're numbered 1, 2, 3. 10 minutes, 2 cores each, 4 gig of RAM each. Q subcommand looks pretty much exactly the same, except here is the job array, -T 1, 2, 3. So that activates array job. Sub task IDs are 1-3, meaning 1, 2, 3. And the script to run is the work script, and the work script needs no parameters because the only thing the work script needs to know is going to be the task ID, which is going to come from the environment variable. We don't pass it here. And the scripts here are for each task are completely self-contained. So there's no parameters to pass here. So all we need to do is kick off the work script. And the work scripts looks like this. The work script is basically a single line, which is to call the right task script, if you like, right? So // here is the name of the task shell scripts, but where the job ID goes, we just use the shell variable SGE task ID, right? So now we're basically going to kick off the correct bash script that corresponds to SGE task ID. That's our task ID from the job2 system by way of the environment variable SGE task ID. What's in the individual task scripts then? We have to actually repeat the pipeline commands now, which is kind of a downside. Or if you look at it, it's an upside because it means that these 3 scripts don't have to have anything to do with each other, right? They could each run completely separate things that are unrelated even. But there we are with our 3 parameters and so on. Okay, so let's kick this off. Okay, now that's going to be an array job. If I'm fast, we'll see it. There we go. Okay, so that's the array job. 1 to 3, stepping by 1, queued and waiting. I'm probably not going to catch it. Oh, so in the moment between there and there, number 1 kicked off and finished. We're not going to catch one of them running. It's going to be too fast. But here you see that number 1 must have kicked off and finished, leaving 2 and 3 left to do. And for some reason, if there's only 2 left, it just does 2, 3 rather than 2-3, whatever. But there we go. Now they're done. There's our logging garbage, all empty. What's our output files? There's another really good. There they are, all good. That is style 3. All right, what about style 4? In style 4, we start making config files, but there's going to be a config file per task. Okay, so let me show you what the config files look like, and then what we build around there. So here we just put each parameter on its own line in the same order, of course, A, B, C, D, E, and then there's 1 config file per task, right? We basically, the advantage here is that we're going to factor out the common stuff from those task 1, task 2, task 3 shell script, which was the pipeline commands, leaving only the rest of the stuff, which was the parameters. And we kind of got rid of the redundancy of having to repeat the kind of the pipeline commands over and over again. So, all right, so how does this look? All right, so we've got the launcher here, which just calls the submit script, right? So, okay. Here's the submit script. As for example, for the job name, we still know that there's 3 tasks here, config 1, 2, 3, same resource usage, same Q sub line with the same -T job array task range, same resource requirements, and we just kick off the work script because again, the parameters are all going to come from like these config files and stuff. and the SG task ID environmental permission, the job system, where there's no other parameters to pass. And so we give the work script no parameters. But what's the work script look like? The work script is going to have to be fancier than the style 3, because it's going to have to pick out the right config file name and then sort of take that config file apart by line. So what's that going to look like? All right, so the work script looks like this. This block of code, which you can kind of take as magic, because we don't really have time to talk about what the IFS shell variable does and how the read shell built-in works. But basically, when you say IFS equals space read -r and a variable name, the shell will read the next line of text from whatever the input is. And here, this curly braces makes this sort of a single block, not a subshell, because with a subshell, we wouldn't be able to modify the shell variables in this script. So the curly braces kind of act like a subshell, but they run the commands inside the current shell. So they're able to affect the current shell's environment. But we curly brace this so that we can do the redirection, reading in from the config file, and that redirection will apply to kind of all of these. The redirection will happen, and then these will run serially, and they'll all be connected to the same file. And so they'll read successive lines of the same file. But anyway, the file name is exactly how you'd see it. This is the beginning of all the config file names, and then we just plug in the SG task ID and so on. And then so that's going to be the current config file to look at, which remember looks like things like this with one line per parameter here. And the reason for the IFS equals and so on is to make sure that if your line has spaces in it, like spaces at the beginning or spaces at the end or funny characters in it, it's all going to come intact without sort of being mangled by the shell. This IFS equals read -r will kind of make sure that nothing gets mangled. There's no parameter expansion, no fancy magic. Just literally read a line. So this reads the next line into shell variable param A, which will happen to be the first line, second line, third line, fourth line, fifth line. So basically the effect of this little block here is to read the first 5 lines of the SG task ID config file into shell variables ABCD, param ABCD. Then once we have the shell variables loaded up, we just do our usual thing. Okay. So all we got to do is kick this off with that. And there's our Java array. Oh, there's 2 running. Number 3 must have been so fast we didn't even catch it. But there we go, done. And here's a bunch of logging stuff, and all empty, of course. And then here's our guys that came out, and there they are, all good. All right. All right. So now I'll just show style 5A and 6A because we're running on time, and you can look at 5B and 5C. The ABCs are a more minor sort of transformation. That's where we move the unvarying parameters, or maybe we'll look at them. We're going to have a Thursday. We're going to do Thursday too, of course. We're just moving where those constant parameters are from what where it's staged there, where they're located. That's a more minor difference than sort of the 5, 6, 1, 2, 3, 4 difference. So let's look at 5A. And in 5A, we just use a single config file. So this is now the Excel kind of thing I was talking about. We have sort of a grid or a table of the parameters. So columns are parameters, rows are tasks, and these need to be tab separated, and so on. So here's what that file looks like. So this is now literally the grid. So it's columns are A, B, C, D, E, rows are task 1, task 2, task 3. Those are tab separated. I can translate the tabs to like underscores or something and make it very clear what the structure is there. The way I've written the shell script, so there's going to be this helper shell script, which is actually does for the first time ever in this workshop. This shell script actually does a bunch of error checking and is pretty careful. And that's because this shell script is universal. You plug this shell script into any style 5 example you want to run. It does not need modification or specialization to any particular task. It's fully general already. And so here I built in all the error checking that you might want to do. There's no time to kind of like really go through this error checking in detail, but that's why it's got so many lines. It's really pretty simple. Maybe on tomorrow I'll just show you the few lines that actually do anything. If you delete all the error checking, there's not much left here. But we'll talk about in a second what this little helper script does. But that helper script is basically going to serve the bridge between this config file and loading up shell variables for the current line in this thing. That's what that shell script's job is to do, is to sort of like you pass in the file name you need, and it knows the SG task ID variable to pay attention to. and then it loads up some shell variables with the appropriate line broken up by tabs. And it's pretty careful. So that, for example, if some of these values had spaces in them, or if they had leading spaces or other weird characters and stuff, they'll all come out parsed correctly. So you really want to be careful with this config file that it's really clean. So, that if you had extra spaces in here or something, they would come across into the shell variables like that. And I say that because if you actually literally do prepare something, a file like this in Excel or something, it's easy to have like extra spaces or like an extra cell in some row or something, whatever. You have to be pretty sure you get this file clean. I could make the script more tolerant, but then it would become less flexible because sometimes you do want like spaces in some of the parameters or stuff. So here it's really careful to actually just take the first part, stop at the tab, then find the next tab, take the part there, and it's very careful to precisely maintain each of those things completely intact so that you can use them with more flexibility than a more permissive thing would be that would allow more stuff to go on without paying attention to it. So anyway, so let's look at this guy. We got the launch script. That's going to call the submit script. But now to make the submit script even a little more flexible, we will pass the submit script a command line parameter, and that is the single config file to pay attention to. That means I could make multiple config files and then kind of run different batch jobs by just pointing the submit script at a different config file. That's sort of convenient, right? We don't have to modify the submit script to kind of adapt it to each little batch we're going to do, or whatever. We can just point it at a different config file and so on. So the one parameter to the submit script is the config file name. Here's what the submit script looks like. The job name will be now style 5A example, same resource requirements. $1, which is the first parameter to the submit script, that's the config file name. So we'll put that in CFG. Now, you could tolerate some more error checking here, like does this config file exist? Is it readable and so on? But to keep this simple for presentation and so on, I just took out all the error checking just to make it more clear what's going on. We need to know how many tasks there are. Well, rather than hard coding in like a 3 or whatever, like some of our other earlier attempts did, we can simply count the number of lines in the config file, and that'll tell us how many jobs there are. So that's what we do. So we do WC-L reading from CFG. This is the command redirection, command substitution that runs this command and takes its output and puts it in the place of this double quoted thing. So n tasks will be, in our case, this is like n tasks equals 3, because it's just number of lines in the config file. I think some white space comes out of this because WC-L, I think it like leaves room for like 5 digits or something at the beginning and spaces, whatever. Anyway, there's some extra white space that comes along with that. If we treat it as arithmetic and add 0 to it, that'll just get rid of the extra white space and whatever. So now it's just n tasks equals 3, single character 3 precisely. That's just kind of nice when we start plugging it in like here, like we don't want extra white space around here. Maybe QSub tolerates that, maybe it doesn't. Anyway, safer just to get rid of the extra white space, which is like adding 0 to it. All right, so now here's our QSub command. Same as always, it's a job array, but now it's 1 to n tasks, where n tasks was the number of lines in the config file. And we kick off the work script. The work script will need to know the config file, because the work script will get the SG task ID from the job system, but that's not the only piece of information you need to know. You also need to know the name of the config file so that you can put them together and pull out the right parameters. So the one parameter that goes to the work script is the config file name. And now we look at the work script. And what is the work script? First parameter and only parameter to the work script is the config file name. We put that in CFG. And then we call this little helper script, which isn't really a shell script proper. I call it instead of .bash, it's a .bashlet, because it's intended to be sourced, not run as an independent shell script. You don't run a separate shell, this thing. It's because this thing needs to modify shell variables in the shell that you're calling it from. Same way our bin activate works in virtual environments. It has to modify the caller shell's environment, so it has to be sourced. And so we source this bashlet. The bashlet is going to do the hard work for you of sort of parsing out the config file. It takes 2 parameters. The first parameter is the config file name, and the second parameter is how many columns you want to pull out. Now, it doesn't actually need that to do its work. This is more like for sanity and error checking. By putting a 5 here, that's our A, B, C, D, E is 5 columns. It's able to check that when it parses out the line, it got precisely 5 values off the line. And then if there are problems, it gives error messages. And then it actually calls exit so that even since it's sourced, and if it calls exit, your script actually stops running. And so basically, if we survive, if we're still alive after calling that source, it means we got exactly 5 parameters off the config file line. So it's very easy to make a malformed config file or something. And so just to make sort of the error checking easier, I mean, you could put that error checking in this script, but sort of why not just embed it into this thing, because it's going to be something you want to do every time. And so that's why I took the 5 here, so that this script can do some error checking for you and verify that the config file line really does have the number of parameters that you expect it does, and it can give you some same diagnostic messages if it doesn't. So yeah, so we expect 5 parameters off that line. And what this script will do is the hard stuff of going to the right line in the config file and parsing it up into the columns and then loading those up into a shell variable and checking that every step of that works and giving nice error messages and exiting out with error, non-zero error statuses if it doesn't go well. Where does it put the parameters? Well, it uses a shell array, which is something we haven't used before, but you know about shell variables. The shell also has arrays. And basically arrays are a variable name, and then you can just use square brackets, as you might expect, because most computer languages that use arrays use square brackets for arrays. And so shell actually bash has 2 kinds of arrays. It has associative arrays and indexed arrays. Indexed arrays are arrays that are the traditional array in most computer languages where the indices are integers. Usually integers starting from either 0 or 1. Probably most computer languages these days start from 0, which really is kind of the right choice. And bash is like that too. So indexed arrays in bash start from index 0, and then the next element is index 1, index 2, and so on. The other kind of array in bash, which we're not going to talk about, is an associative array, which is kind of like a hash table in other languages and so on. The indices can be strings. And so you can index by a string, and then the value is another string, which is kind of, it would be what's a hash in Perl, or some languages call them associations, or whatever. But it's basically a key value kind of thing. But here what we're going to use is indexed arrays, and this bashlet puts the 5, in this case 5 parameters, into a shell array called params, and the elements just get loaded up in that order. So the first through the 5th columns of that line, the appropriate line, the SVG task ID line, go into params bracket 0, 1, 2, 3, 4. So here we do the usual thing, which is here they're kind of named by position, but you really want to write your pipeline commands with the parameter names in a way that makes sense, especially if you start inserting and deleting columns and stuff. So we just pull out 0, 1, 2, 3, 4 and rename them A, B, C, D, E, and then we have our usual business down here. So yeah, we'll maybe take a quick peek at the bashlet tomorrow or something, but we don't need to understand the bashlet to use it. So here is the way we kick this off. All right. And out. You can see that May 2, 1:50 p.m. This is when I last moved the log stuff here, but you can see definitely that the outputs are from just now, May 3 at 4:30, and they do have the right output. So that is style 5A, and then style 5B and stuff and 5C just move those constant parameters into different places, like either push them into the whatever. So all right, so it's kind of that's kind of out of time. We do have tomorrow, so we can stop here, talk about style 6 tomorrow. But the idea here is that these are kind of like templates. These are pretty easy. You can copy one of these directories to a new copy, and then kind of change the work script and whatever parameters make sense for you, and adapt these to whatever project situation you have. These are intended to be fairly easy for you to modify to whatever situation you need to run. And you have the summary table in the slides. So here's the table that kind of summarizes, and you can just look at this, and some of these styles maybe you think, oh, I would never do it that way, or like maybe like some of the others it's like, well, maybe, and then it just depends on your situation, kind of which one would be the one you want to use. But sort of like you can use this table to sort of like make your choice as to what style you want. Copy this directory, the appropriate directory, to a new directory, and then edit the files to modify which parameters are, how many parameters, what they're called, and what the actual commands are that are going to kick off to start the analysis. And in that way, you can adapt any of these things to whatever situation you need for your own work. Okay, so we'll see you tomorrow.